Imagine walking across a dried-up lakebed in New Mexico. The ground is cracked, pale, endless in every direction. And then you see them, footprints, dozens of them, small ones, big ones, pressed into ground that used to be soft mud on the edge of an ancient lake. At first glance, they look like they could have been left yesterday. Somebody's kid ran through wet clay. Someone's dog followed behind. Except these prints weren't left yesterday. According to the scientists who found them, they were left over 21,000 years ago, during the last ice age, thousands of years before anyone thought humans were supposed to be here. If that's true, it doesn't just add a footnote to the history books. It rips out an entire chapter and rewrites it. For decades, the story of how humans arrived in North America was locked in place. A tidy timeline, roughly 13,000 years ago, ice-free corridors, a culture called Clovis, first in, first to spread across 2 continents. Textbooks taught it, museums built exhibits around it, and then a set of footprints in the New Mexico desert threatened to blow the whole thing wide open. So here's the question we're chasing today. Are these prints real, credible evidence that people were walking around North America 10,000 years earlier than we believed? Or is there some other explanation? Some flaw in the dating, some trick of geology that would put everything right back where it started? We're going to dig into this properly, where these tracks came from and how they were even discovered in the first place. How scientists tried to figure out their age using something as delicate as ancient seeds buried in the mud. Why other researchers push back hard, accusing the original team of getting fooled by what's called the old carbon problem. And what happened when independent scientists, using completely different methods, tried to settle the argument once and for all. By the end, you'll know what most experts now agree on, where the real disagreement still lives, and why white sands might be one of the strangest, most convincing pieces of evidence in the entire story of how humans reached this continent. Before we get into it, tell me where you're listening from and what time it is right now. I love checking the comments and seeing this thing lighting up all over the map. Sydney at sunrise, Chicago at midnight, London somewhere in between. It's one of my favourite parts of putting these out into the world. And if you want to support the channel, the easiest way is to follow on Spotify. It's completely free. It gets you ad-free listening and it genuinely helps more than almost anything else I could ask for. If you're already there, dropping a 5-star review takes about 10 seconds and makes a real difference. Links in the description if you want to go do that right now. Alright, footprints in ancient mud, a 10,000-year gap in human history. A scientific fight that's still going on right now. Let's start at the beginning, back when everyone thought they already knew the answer. For most of the 20th century, if you asked an archaeologist how humans got to North America, you'd get the same answer, delivered with the kind of confidence usually reserved for facts like gravity or the boiling point of water. About 13,000 years ago, give or take a few centuries, small groups of hunters crossed a land bridge from Siberia into Alaska. The ice sheets that had locked up most of Canada finally started to crack open, forming what's called an ice-free corridor. And through that corridor walked the first Americans, carrying with them a very specific, very recognizable set of stone tools. Those tools have a name, Clovis, named after Clovis, New Mexico, where they were first identified back in the 1930s. Beautifully crafted spear points, fluted at the base, sharp enough to bring down a woolly mammoth. And for decades, wherever archaeologists found Clovis points, they found them at the bottom of the story, the oldest layer, the founding culture, the first chapter. This became known as the Clovis-first model, and it wasn't just a theory floating around in academic journals. It was the theory. Textbooks taught it as settled fact. Museums built entire exhibits around it. Documentaries opened with the same triumphant narrative. Brave hunters crossing in frozen wilderness, entering an empty continent teeming with megafauna, and spreading across two entire landmasses in the blink of an evolutionary eye. And honestly, it made a certain kind of sense. Clovis points showed up at sites across North America with remarkable consistency. The dates clustered tightly around 13,000 years ago. No older, reliable, undisputed sites seemed to exist. Every time someone claimed to find something earlier, the evidence had a way of falling apart under scrutiny. Bad dating, contaminated samples, natural rock formations mistaken for tools. The Clovis-first model wasn't just popular, it was defended fiercely, almost like a wall that archaeology had built and didn't want anyone knocking down. But walls like that, no matter how solid they look, tend to develop cracks eventually. Starting in the 1970s and accelerating through the 80s and 90s, a small number of researchers began finding sites that just didn't fit. A place in southern Chile called Monteverde produced evidence of human habitation that appeared to predate Clovis by over 1,000 years. Stone tools, remains of what looked like animal hide dwellings, even preserved plant material. The site was excavated meticulously, dated repeatedly, and defended by its lead archaeologist for nearly 2 decades against fierce criticism. It wasn't an easy fight. Entire academic careers had been built on the Clovis-first model. Accepting an older site meant admitting the foundational story of American archaeology was wrong, and that's never a comfortable thing for a field to swallow. But slowly, painstakingly, the evidence from Monteverde and a handful of other sites started chipping away at the wall. By the early 2000s, most archaeologists had accepted that pre-Clovis people existed, humans who arrived in the Americas before that 13,000-year mark. Not by a huge margin, maybe 1,000, 2,000 years earlier. Enough to rewrite some textbooks, but not enough to completely upend the field. This is where the term pre-Clovis comes from, and it's worth understanding what it actually means. It's not a specific culture or a specific group of people the way Clovis is. It's more like a category, a placeholder for anything that predates the old benchmark. Pre-Clovis sites tend to be sparse, controversial, and often built on frustratingly thin evidence. A scattering of stone flakes here. A hint of ancient hearths there. Enough to suggest human presence, but rarely enough to prove it beyond reasonable doubt. So by the time white sands entered the conversation, archaeology had already stretched its comfort zone once. People arriving before Clovis wasn't the heresy it used to be. But here's where you need to understand the scale of what White Sands was claiming. Monteverde pushed the timeline back roughly 1,000 years. Other pre-Clovis candidates suggested similar modest adjustments. White Sands wasn't asking for 1,000 years. It was asking for 10,000. 10,000 years earlier than the old Clovis benchmark doesn't just tweak the story. It rewrites the entire opening chapter. If the footprints were really 21,000 to 23,000 years old, as the original research team claimed, that would place humans in North America during the height of the last ice age, when massive ice sheets should have made that ice-free corridor completely impassable. It would mean people were here thousands of years before Clovis even existed as a culture. It would mean the entire framework archaeologists had used for nearly a century, even the updated pre-Clovis adjusted version, was still fundamentally wrong about the timeline. That's not a footnote. That's a different book entirely. Now, before we go further, it's worth pausing to ask a simple but important question. What actually counts as strong evidence for something like this? Because not all evidence is created equal, and archaeology has learned that lesson the hard way over and over again. Stone tools can be strong evidence, but only if they're clearly human-made and reliably dated. Bones can help, especially if they show cut marks or were found alongside artifacts. DNA has become an incredibly powerful tool in recent years, capable of tracing migration patterns across thousands of years with remarkable precision. And then there are sites themselves, places with layered evidence, hearths, tools, food remains, that together build a convincing picture of sustained human activity. Footprints occupy a strange and fascinating category all their own. They're not artifacts in the traditional sense. Nobody carved them. Nobody left them behind as a tool for future use. They're something more immediate, more visceral. A footprint is direct, undeniable physical evidence that a living, breathing human being stood in that exact spot at that exact moment. You can't fake the biomechanics of a human gait. You can't easily mistake a child's footprint pressed into ancient mud for some random rock formation. But direct as they are, footprints come with their own problem. Dating them precisely is incredibly difficult, because a footprint itself doesn't carry a date stamp. You have to date the material around it, the layers above and below, and hope that material tells you something trustworthy. Which brings us to the real challenge facing the White Sands research team. An extraordinary claim, footprints pushing human presence in North America back by 10,000 years, needed extraordinary documentation to back it up. Not a single date from a single sample. Not one convenient layer of sediment. It needed multiple independent lines of evidence, all pointing in the same direction, all withstanding the kind of scrutiny that had already destroyed dozens of earlier pre-Clovis claims. Because if White Sands was going to survive the fight that was coming, and it was absolutely going to be a fight, it needed to be built on something far more solid than a single carbon date and a hopeful headline. To understand why those footprints at White Sands matter, you first have to understand the place that made them possible in the first place. Today, if you drive into southern New Mexico's Tularosa Basin, it does not scream Ice Age wetland. It looks more like the set of an alien planet. Blinding white dunes, rippling like frozen waves, sparse desert plants, heat that makes the horizon shimmer. This is White Sands National Park, home to the largest gypsum dune field on Earth. But roll the clock back 20,000 years, and the basin is unrecognizable. During the last ice age, the climate was cooler, and in this part of the world, often wetter. The Tularosa Basin is a closed basin, basically a giant bowl with no river flowing out of it. Water that comes in, rain, snowmelt, streams from the surrounding mountains, has only two options: soak into the ground or sit there and evaporate. In the Pleistocene, that water didn't just sit in a few shallow ponds. It pooled into a vast lake, Lake Otero. Imagine a body of water stretching for hundreds of square kilometres, filling much of the basin floor. Around its edges, marshes, wetlands, muddy flats, and shallow inlets where animals came to drink and forage. It wasn't an empty desert. It was a productive, messy, living landscape. And like any lake in a dry basin, Lake Otero didn't stay the same size. Its shoreline advanced and retreated over thousands of years as climate shifted. Colder, wetter periods filled it. Warmer, drier spells shrank it back into smaller basins and scattered ponds. Every time the shoreline moved, it left behind belts of soft, saturated sediment that would dry, crack, get wet again, and repeat. Those shifting margins are where the magic happens. Stand on that ancient shoreline at the right moment in time. The lake level has dropped just enough to expose a broad, flat mudflat. The surface is wet, but not soupy, firm enough to walk on, but soft enough to take an impression. A human steps out onto it. Then another, maybe a child, runs ahead, leaving smaller, shallower tracks. A mammoth trundles along nearby. A giant ground sloth lumbers through a different patch of mud. Each of those steps presses down on that thin skin of wet sediment, deforming not just the surface, but the layers beneath it. You can think of it like pushing your finger into a stack of soft pancakes. The imprint runs deeper than what you can see on top. Now, here's the critical part. If the mud stays wet for too long, the impressions slump and vanish as the sediment flows back into place. If it dries and then gets churned up by waves, wind, or more traffic, the tracks get obliterated. To preserve a clean snapshot, a single moment where you can say someone walked here, in this order, in this direction, you need a very particular sequence. First, the right kind of mudflat, then the footprints. Then, relatively quickly, a layer of new sediment that covers and protects them. At White Sands, that new sediment often came from the same thing that gives the landscape its modern name, gypsum. The surrounding mountains are rich in minerals. Water dissolves gypsum from those rocks and carries it into the basin. Because there's no outlet, the dissolved minerals just accumulate. As Lake Otero and its successor ponds evaporated under the New Mexico sun, they left behind crusts of gypsum. Wind and water broke those crusts into tiny crystals and grains. Over time, these grains were blown into dunes, swept into shallow pools, or washed as thin sheets across the wet shoreline. When a fresh film of gypsum-rich silt washed over a trackway, it could do something incredibly important. It could seal it. A wet print, covered by a slightly different, slightly drier layer, turns into a little stratigraphic sandwich. Print in the middle, older mud below, younger sediment above. This is what geologists and archaeologists mean when they talk about stratigraphy. Layers. One on top of another, each layer representing a different episode. Wetter, drier, deeper lake, shallower lake. If conditions cycle wet period, mud flat, prints dry period, wind-blown sand, then wet again, you can build up a vertical stack of these snapshots. In the Tularosa Basin, those stacks record thousands of years of lake level changes, shoreline positions, and surface conditions. Some layers are featureless mud, others hold the faint outlines of old root mats or polygonal cracks from drying. And some, if you're very lucky, hold footprints, mammoth, sloth, camel, bird, and sometimes humans. The surfaces where many of the White Sands tracks are found today are called playas. A playa is basically the dead flat floor of a dried lake. In wet seasons it can turn into a shallow sheet of water or a sticky, treacherous mud. In dry seasons it hardens into a crust that can look deceptively smooth and empty. Under that crust, though, is a stratified record of all those wet-dry cycles. Gypsum plays a strange double role here. It helps preserve footprints in the subsurface, but it also contributes to their fragility once they're exposed. Those ancient track-bearing layers were buried for thousands of years, protected in the dark. As modern erosion and wind strip off the overlying sediments, they come back to the surface. Suddenly they're facing sunlight, wind, and modern rain again. The result is haunting and temporary. On some playa surfaces you can see perfect trackways marching across the ground when the moisture is just right. A little rain can darken the compacted sediment inside the prints, making them stand out. A few dry, windy days later, they can fade back into near invisibility or begin to crumble away. This is why careful documentation matters so much. When researchers at White Sands find a trackway, they're not just looking at something old. They're often looking at something that may only be clearly visible for days or weeks under current surface conditions. If they don't map it, photograph it, and record its position in the layer cake of sediments, it can be lost, literally blown away, before anyone has a chance to study it in detail. But when they do get to it in time, the payoff is extraordinary. Because this landscape doesn't just preserve isolated human footprints floating in geological nowhere. It preserves an entire Ice Age community written in tracks. On a single surface you can find humans walking one way, mammoths another, sloths circling or doubling back, canids stalking along the margin, birds clustering near shallow pools. Layer by layer. These player sediments capture moments when whole ecosystems converged on the shrinking shores of Lake Otero. That's the trap White Sands sets. Not a trap for animals or for people, but a preservation trap. A specific combination of basin geometry, fluctuating lake levels, gypsum-rich water, and repeating wet-dry cycles that occasionally freeze living motion into the ground. For a few brief minutes, mud becomes memory. Then gypsum and time lock that memory away. And it's inside that delicate layered memory, those stacked footprints of an entire Ice Age shoreline, that the White Sands team would eventually find something so provocative it forced archaeologists to rethink when, and maybe how, humans first walked onto this continent. The strange thing is, for a long time, nobody was out there looking for Ice Age footprints. White Sands was already famous for missiles. Most of the player in Dunefield sits inside White Sands Missile Range, one of the largest military installations in the United States. Since World War II, this has been a place where rockets are tested, drones are flown, and things you don't get to ask many questions about go up, explode, or come crashing back down. There were scattered reports going back decades of weird marks or ancient tracks on the player surfaces. Ranchers and soldiers had noticed them long before any big paper in science. Sometimes you'd get stories of giant bird tracks or dinosaur footprints showing up after a rain and then disappearing again. People saw them, but they were curiosities, not data. The crucial shift came when a few paleontologists and park scientists realized that this disappearing act wasn't a nuisance. It was a clue. If tracks were appearing only under certain moisture conditions, then vanishing, that meant two things. First, there had to be buried surfaces preserving them below. Second, the player wasn't a static tabletop. It was a dynamic, eroding cross-section through time. Every storm, every dry spell, was peeling back one more page of the book. That's where systematic surveying came in. Instead of waiting for a random footprint to pop out and surprise someone driving across the basin, researchers began walking transects, slow, methodical grids, eyes scanning for the slightest tonal change on the ground, a faint oval, slightly darker than its surroundings, a linear pattern of depressions that curved just enough to hint at a gate. They weren't just roaming the park, they had to operate inside an active missile range. That meant clearance, schedules, convoys. You don't just wander wherever you like on a landscape where unexploded ordnance is a non-zero possibility, and test schedules are classified. Field days had to be coordinated with the army. Some areas were completely off limits. Others were accessible only in narrow windows between tests, or had to be cleared in the morning and vacated by a precise time. It's hard enough to do delicate stratigraphic work when the biggest threat is a thunderstorm. At White Sands, you're doing it while making sure your excavation pit isn't in the line of fire for a rocket test. So the pace was dictated by two forces, erosion from above and permissions from the side. Even with those constraints, chance still played a huge role. A particularly wet monsoon season might flood portions of the player, saturating the upper layers. Then a spell of dry weather would harden the surface. As the water wicked upward and evaporated, the compacted sediments inside old footprints would dry at a different rate than the surrounding matrix. For a brief window, trackways that had been invisible for years would materialize like ghosts. Park staff, trained to recognize these ephemeral patterns, started flagging them. A ranger might call the research team, "Hey, the North player is popping today. You need to see this." The scientists would scramble, get clearance, roll in with GPS units, notebooks and flags, trying to outrun the sun and the wind. But here's the thing, a single photogenic footprint isn't enough. Early on, a few prints were photographed. Ovals that looked human-ish, toes vaguely visible. They're compelling to the eye. But if all you have is a picture of a depression in mud, you don't have proof. You have a Rorschach test. Animal prints can erode into human-like shapes. Cracks, mud curls, and gas escape structures can mimic heel and toe outlines. Even modern boot prints, softened by weathering, can masquerade as something older, if you don't know exactly where they sit in the sediment stack. To move from that looks human to this is a human footprint from a specific time, you need context. So the team started cutting sections, not just scraping around the print, but trenching down beside it to see the layers. Where precisely in the stratigraphic sandwich did that track sit? What lay above it? What lay below? Were there plant remains, seeds, rootlets, pollen anchoring that surface in time? Were there micro cracks that told you the mud had dried before the next layer came in? Were there any intrusive features, burrows, roots, modern cracks that might have distorted the record? They also needed to establish the trackways as trackways, not isolated shapes. One depression could be almost anything. 10, 20, 50 depressions aligned along a path, each the right distance apart, each varying in depth and pressure in ways that match how a human actually walks. That's different, so they mapped them, painstakingly. Every footprint got a coordinate, a number, a set of measurements, length, width, orientation, inferred left or right foot. When you plot those points, patterns emerge, step length and stride length reveal estimated height. Variations in depth indicate changes in speed or load. Slight zigzags show course corrections. Overlapping tracks reveal sequences. Who walked first, who came after, who stepped in whose footprints. That's when the true scale of the discovery started to become clear. This wasn't a single human stepping in some lucky patch of mud. Across the playa, researchers began finding multiple track-bearing surfaces stacked at different levels in the sediment. On one layer, a series of human prints paralleling mammoth tracks. On another, human footprints interleaved with giant ground sloth paths. Elsewhere, small human footprints, children or adolescents, darting between larger ones. In some places, these surfaces extended for hundreds of meters. Paths that crossed, converged, or ran side by side. Not one moment but many, not one journey but repeated use of the same general shoreline corridors as the lake level rose and fell over centuries. And the basin itself kept helping and hindering in equal measure. Every time the wind stripped off another few millimeters of gypsum-rich sediment, a different slice of the past came into view. A trackway traced one year might be gone the next, its surface flaked away, while a new line of prints appeared just upslope. It's like watching a slow-motion archaeological conveyor belt, old surfaces riding upward into the zone of visibility, pausing briefly where human eyes can find them, then crumbling away while deeper layers take their place. This rolling exposure is what turned White Sands from a curiosity into a trackway treasure, because it meant researchers weren't stuck with a single chance find. They could return, season after season, watching new stretches of ancient shoreline emerge. They could link separate track segments found years apart into continuous paths once the intervening ground eroded. They could see, literally in cross-section, that there were multiple generations of track-bearing layers, each with its own community of humans and megafauna frozen into it. And once those trackways were firmly established as human, by their shape, their biomechanics, and their stratigraphic position, one question loomed over all the others. Exactly how old were they? So what actually makes a footprint human, as opposed to just a suggestive smear in the mud? Start with how you walk. Humans are heel strickers. When you take a step, your heel hits first. Then your weight rolls forward along the lateral edge of your foot, across the ball, and finally off the big toe. That movement leaves a very specific pressure pattern in soft sediment. In the clearest white sands prints, you can see it. A well-defined, slightly deeper heel cup, a midfoot region that's not just a flat blur but subtly arched, less pressure along the inside where your foot arches, more along the outside edge. Then a forefoot where the impressions of the toes fan out, with the big toe often leaving the deepest, longest mark. That toe splay is important. Human toes, especially on bare feet, spread out when they push off. The big toe is in line with the rest of the foot, not set off to the side like in many primates. In some of the best preserved prints, the big toe impression is almost like a little comma, showing where it dug in and then released. The smaller toes are shallower and more variable, but still lined up across the front. Compare that to, say, a big cat or a canid. They're digitigrade, they walk on their toes. No big flattened heel impression, no long metatarsal segment. Very different pressure distribution. Hoofed animals, you get a split or single hoof, not a broad plantigrade pad. Giant ground sloths, mammoths, camels, all of them have their own distinctive geometry, and at white sands those are preserved too. You can literally walk from one kind of track to another and watch the anatomy change under your boots. But anatomy isn't always obvious. Mud lies. The sediments at white sands are mostly fine-grained gypsum. Depending on how wet or dry they are, they can behave very differently when something steps on them. Too wet, and the foot sloshes down, water squirts up, and the edges collapse. You lose crisp toe outlines. Too dry, and the surface can fracture, creating polygonal cracks that look bizarrely footprint-ish until you realise they don't line up into any sensible path. In between, you can get curl-up of thin mud flakes around a depression, or little ridges along the margin where displaced sediment rebounds. Those distortions can create false toes or smooth out what were once sharp features. An animal stepping into a partially dried hoofprint can squash it into something more oval. A gas bubble escaping from saturated mud can leave a rounded pit with a raised edge that in the right light could pass for a heel. This is why researchers don't just look at one print and declare victory. They look at the trackway logic. A human doesn't just leave a shape, they leave a pattern of movement. Left, right, consistent step length, regular cadence. A centre line that isn't perfectly straight, but wobbles within a narrow corridor the way a person naturally does as they walk. At white sands, the human trackways show that rhythmic alternation. The spacing between footprints falls into ranges that match the expected stride for people of particular estimated heights. The angle of each foot relative to the direction of travel, called the gait angle, falls within human norms, a slight outward towing for some individuals, straighter for others, but not the wildly splayed orientations you'd get from an animal zigzagging on four legs. You can also see changes within the same trail that make biomechanical sense. Sections where the steps get shorter and deeper, as if the person was slowing down or slogging through softer mud. Places where a heel doesn't sink as far, but the toe digs in more deeply, suggesting a brief acceleration. Occasional slips where the heel skids forward a bit before the forefoot catches. These aren't random distortions, they're the physics of a biped walking through real terrain. To capture all of that, the scientists don't trust eyeballs alone. They use photogrammetry, taking dozens, sometimes hundreds, of overlapping high-resolution photos from different angles, then feeding them into software that reconstructs a precise 3D model of the surface. Every little bump and hollow is recorded as a cloud of points accurate to millimeters or better. With those 3D models, you can rotate the print, slice cross-sections through it, run heat map-style analyses of depth and slope, and compare it quantitatively to modern human footprints made in controlled conditions. You can measure arch depth, heel width, toe lengths, and pressure distributions, rather than just saying, "Yeah, looks pretty human." In some cases, they also make physical casts, pouring dental stone or other casting materials into the prints when conditions allow, then taking those hardened replicas back to the lab. Casts let you handle the footprint, turn it in your hands, compare it directly to casts of known animal and human prints. But they're used sparingly. The prints are fragile, and every intervention has to be weighed against the risk of damaging the site. Out of this work comes a kind of confidence spectrum. On one end you have textbook human prints, clear heel, clear arch region, clearly separated toes with the right proportions, embedded in a trackway with impeccable left-right alternation and human-like stride. These are the ones you can put in a paper figure without much controversy. In the middle are prints that are part of a convincing trackway, but each individual depression is a bit degraded, edges worn, toes blurred, maybe some overprinting by later animals. On their own, any given print might be ambiguous, but as part of a consistent series, they add weight to the interpretation. On the far end are marginal impressions, shallow ovals, partial depressions, weird shapes at the edge of eroded surfaces. These might be flagged in the field but treated cautiously. Sometimes they're set aside as indeterminate, not enough information to call them human, but still data points in understanding how the surface formed and eroded. This graded approach is crucial because it feeds into a broader point why trackways can be more persuasive than isolated artifacts in a messy, eroding basin. A single stone flake found on the surface of a player could be almost anything. It might be a genuine tool. It might be a geofact produced by natural breakage. Even if you're sure it's a tool, pinning it to a precise moment in time can be tricky if it's been moved or reworked. A trackway, by contrast, is behaviour frozen in place. Dozens of footsteps laid down over minutes, maybe hours. Each one anchored to the exact surface where it was made. The spatial pattern encodes anatomy, gait, speed, direction, even social context when multiple people are moving together. You're not just seeing that a human was somewhere in this landscape at some vague point. You're seeing that a human walked right here, in this direction, at this pace, when that particular layer of mud was wet and the lake was at that particular level. At white sands, that's the power of the footprints. They aren't just human-shaped holes in the ground. They're chains of evidence, anatomical, biomechanical, and stratigraphic, all pointing to the same conclusion. And once you're confident about who made them and how they moved, the next question becomes unavoidable. When exactly did they walk? When the first dating results came back from white sands, they didn't just quietly nudge the North American timeline. They threw a grenade into it. The team reported ages clustering around 23,000 years ago. Some samples a little older, some a little younger. A spread roughly from 21 to 23,500 radiocarbon years before present, which, once you run them through calibration curves, translates to about 23 to 26,000 calendar years ago. That matters because of what was going on then. This is smack in the middle of the last glacial maximum, the coldest, iciest peak of the last ice age. The big continental ice sheets over North America were near their maximum extent. In the traditional story, humans don't reach the interior of North America until after those ice sheets start retreating, after about 16,000 years ago, and the Clovis culture, the supposed first big cultural footprint, doesn't show up until about 13,000. So if you have clearly human tracks on the floor of an ancient lake in what's now New Mexico, and you can tie those tracks to layers dating around 23,000 years ago, you've just pushed the minimum people were here date back by roughly 10,000 years. Not as a rumour or a disputed stone flake, but as entire families walking across a lakeshore while mammoths grazed nearby. But there's an important subtlety. They didn't date the footprints themselves. You can't. A footprint is mostly displaced sediment and void. There's no inherent clock inside the depression. What you can date is the stuff that got buried with it and around it. At White Sands, that stuff was mainly plant material, seeds and bits of aquatic plants called rupia, tiny remains from the ancient lake ecosystem. The track-bearing surface sits as a thin, distinctive layer within a stack of lake deposits, muds, silts, and other flat-lying sediments laid down over thousands of years as the water level rose and fell. Imagine a layer cake. Somewhere in the middle is a frosting layer that preserves a perfect trail of human footprints. Directly underneath is another older layer of lake mud. Directly above another younger layer. In both of those neighbouring layers you can sometimes find seeds embedded in place, still nestled in the same fine sediment they fell into when they died. Those seeds contain carbon, and carbon can be dated. Radiocarbon dating starts with a simple idea. Cosmic rays in the upper atmosphere turn nitrogen into a radioactive form of carbon called carbon-14. Living things constantly take in carbon through photosynthesis if they're plants, by eating plants or other animals if they're animals. As long as something is alive, carbon-14 is being replaced. When it dies, that intake stops. The carbon-14 in its tissues starts to decay at a known rate, ticking down like a slow nuclear hourglass. By measuring how much carbon-14 is left in a dead plant or animal, and comparing it to the amount you'd expect if it were freshly dead, you can estimate how long ago it stopped exchanging carbon with the atmosphere. For organic material up to about 50,000 years old, radiocarbon is our workhorse dating method. But it doesn't give you a single magic number. A lab returns an age estimate with uncertainty, something like 21,000 plus or more 400 radiocarbon years before present. That plus-minus is not a rounding error. It's a statement about noise in the measurement, variability in the original carbon, and assumptions in the decay model. And you can't stop there. The amount of carbon-14 in the atmosphere has not been perfectly constant through time. Solar activity, Earth's magnetic field, even human activity in the very recent past, all of these tweak the background levels. So archaeologists use calibration curves, built from things like tree rings and corals whose true calendar ages are independently known. Those curves translate a radiocarbon age into a calendar age range, often a wiggly, multi-peaked probability distribution rather than a single date. This is why serious papers don't say, "We dated the footprints to 23,420 years ago." They say the layer immediately overlying the footprints yielded plant macrofossils dated to between X and Y calibrated years before present, at 95% confidence, and so on. It's all about ranges and probabilities. Now tie that back to the footprints. At White Sands, the argument is contextual. If you have a human track surface sandwiched between two layers that both date to around 23,000 years ago, and the stratigraphy is clean, no signs that the layers have been churned up or inverted, that sandwich becomes a powerful constraint. The footprints must be younger than whatever is beneath them. They must be older than whatever sealed them from above. If both those bracketing layers fall in the last glacial maximum, then so did the footprints, even if you never date a single grain of sediment from inside a toe impression. Context becomes everything. You want surfaces that are sealed. Once the prints were made, they were quickly buried by new sediment and protected from later disturbance. You want layers that can be traced laterally, so you're sure the seed you dated and the footprint you're excited about really do belong to the same snapshot in the lake's history, not to different pockets that just look similar. You want to see the story in the layers, older lakebeds below the footprint horizon, younger lakebeds above, all in the correct order with no weird folding, faulting or deep burrowing animals to scramble the stack. Even when all of that looks good, there are still uncertainties. Calibration curves sometimes give broad or even multi-part ranges. A given radiocarbon measurement might be compatible with two slightly different calendar intervals because of wiggles in past carbon-14 production. Different labs might measure slightly different values from nominally similar samples. And the older you get, 20, 30, 40,000 years, the more those uncertainties stretch. That's where the upcoming debate starts to heat up. Because radiocarbon doesn't just depend on decay, it depends on what kind of carbon you started with, and whether that carbon has been altered or contaminated. Were the dated seeds really growing in equilibrium with the atmosphere? Or were they drawing carbon from old groundwater with a different radiocarbon signature? Could tiny bits of younger rootlets or microbes have snuck into the samples and made them look artificially young? Could dissolved ancient carbon in the lake, the so-called reservoir effect, have made them look too old? And are the seeds you chose really the best things to date? Or do different kinds of samples from the same layers tell slightly different stories? Those questions don't overturn the big claim by themselves, but they matter. In the next sections, we'll dig into exactly how the White Sands team did their dating, why they trusted those last glacial maximum ages, and why other researchers immediately started probing their choices, looking for any hidden biases in the clock that seemed to show humans walking across New Mexico 10,000 years too early. So, what did they actually do at White Sands? How do you take a lakebed full of footprints and turn it into a timeline? You start tiny. The workhorses here were Ruppia seeds. Ruppia is an aquatic plant, ditch grass that grows in shallow, quiet water. In Lake Otero, 20-odd thousand years ago, it was part of the normal lake ecosystem. Each season, plants would grow, flower, drop seeds, and die. Some of those seeds would drift down into the mud and get buried. Those seeds are small, but they're carbon-rich, and they're short-lived. A Ruppia plant isn't tapping some deep, ancient carbon pool. It's pulling carbon straight from the water, which, in a shallow, wind-mixed lake, should be closely linked to the atmosphere. In principle, a Ruppia seed is about as close as you can get to a this year's carbon timestamp for that lake surface. The team took advantage of that. They didn't just scrape up a handful of mud from somewhere near the prints and send it to a lab. They excavated the trackways in vertical profiles, exposing the stack of lake beds like slices in that layer cake. Then they very deliberately sampled multiple horizons above and below the footprint layers. Think of it like coring a sandwich, not stabbing it once with a fork. You've got the footprint horizon, where the toes and heels actually distort the sediment. Directly above that, a slightly younger layer of lake mud. Above that, another and another. The same below, one layer down, 2 layers down, 4 layers down. From each of these distinct flat-lying strata, they picked out Ruppia seeds and other plant bits, cleaned them and ran them through radiocarbon dating. The critical idea is stratigraphic ordering. If the system is behaving nicely, deeper layers should always be older than shallower ones. It's basic geology, first in, first buried. When you line up your radiocarbon dates from bottom to top, you want to see them stack in a logical way. Older at the base, getting progressively younger as you approach the surface, with overlapping error bars that still respect that order. At White Sands, that's largely what they reported. Dates from below the track surfaces cluster in one window. Dates just above those same track surfaces cluster slightly younger, but still in the last glacial maximum range. Go several layers up, and you inch toward younger values. The curve of ages through the profile tends to slope the right way. That kind of consistency is important. One glamorous date from right above a spectacular footprint tells you something, but it's fragile. If that one sample turns out to have a rootlet in it, or a lab error, your whole story collapses. A whole staircase of dates marching in order through the sediments is much harder to topple with a single criticism. It also lets you treat the footprint horizon as a bracketed interval, not a magic number. If the layer below the prints is, say, 23.5 to 25,000 calibrated years ago, and the layer above is 22.5 to 24,000, then the footsteps themselves must fall somewhere in between those ranges. You don't know the exact year, but you know the general window, and the more tightly those brackets pinch together, the more constrained that window becomes. But this ideal picture, perfectly stacked ages, neat layer cake, is just that, ideal. Real sediments are messy, seeds are tiny, they can move. A footprint surface is a disturbed surface by definition. A human or a mammoth or a giant ground sloth walks across soft mud and churns it up. When the next thin film of sediment settles on top, a few seeds from that newer layer might trickle down into the print hollows. Later, as the lake level changes, burrowing organisms or plant roots can mix the upper layers. Cracks can open as mud dries, and then fill with younger material when it floods again. All of that creates opportunities for reworking. A seed that grew and died thousands of years after the prints were made could be physically relocated downwards into older mud, or sideways into a layer that looks similar but is subtly different. When you date that seed, the radiocarbon machine has no idea it's an intruder. It just reports an age. That's why the White Sands team didn't rely on a single seed from each horizon. They tried to date multiple plant macrofossils from multiple positions, sometimes repeating dates from the same nominal layer. If one outlier pops up, an age that doesn't fit the stratigraphic sequence, you can flag it as probably reworked or contaminated. If 3 or 4 independent samples from the same layer give you comparable results, and the layers above and below behave in an orderly way, your confidence grows. Repeated sampling also lets you see patterns through time, not just a snapshot. When the team extended this approach through multiple footprint-bearing layers, they saw that human tracks weren't limited to a single magical people showed up one summer and vanished horizon. There are track surfaces separated vertically by sediments that themselves represent years to centuries of lake history. Some of those other horizons also have associated Rupia seeds dated in the same broad last glacial maximum window. That suggests something more interesting than a one-off visit. It points to repeated human use of the lakeshore as the Ice Age dragged on. People came back to this place or others like it along the shoreline, again and again over a span of time that might stretch across centuries or longer, leaving trackways in layer after layer as the lake level shifted and the mud alternately dried and reflooded. In other words, the time sandwich isn't just one neat slice. It's a stacked deli tray, multiple footprint layers, each with their own brackets, all clustering in that same cold glacial interval. The seeds help define the bread, the before and after for each track surface. The overall pattern of ages, when they mostly line up in order, tells you the sandwich hasn't been turned upside down. That's the logic that underpins the bold claim: if the seeds are trustworthy indicators of atmospheric radiocarbon, if their positions in the stratigraphy really do mark the moments when they fell, then the people who left those prints were walking around New Mexico while ice sheets towered across much of the continent. Of course, each one of those ifs is debatable, and critics quickly zeroed in on exactly that. Are Rupia seeds in a shallow changing lake really that simple to interpret? Could the carbon inside them be older than the plants themselves? That's where the reservoir effect and the whole argument over old carbon comes in. To understand the criticism, you have to shift your focus from seeds and footprints to the lake itself. Radiocarbon dating assumes that the thing you're dating was built from carbon that matched the atmosphere at the time it was alive. But not all carbon pools are equal, and not all of them are in sync with the air. That's where reservoir effects come in. A reservoir effect is what happens when an organism is pulling carbon from a source that's out of date relative to the atmosphere. Marine organisms are the classic example. Deep ocean water can sit around for hundreds to thousands of years before it mixes back to the surface. The dissolved carbon in that water has been cut off from the atmosphere for a long time. So when a shellfish builds its shell from that carbon, the shell can look centuries older than it really is when you radiocarbon date it. Freshwater systems can have their own versions of this, especially if they're fed by groundwater that has been circulating through carbonate rocks, limestone for example. As that water dissolves the rock, it picks up plenty of carbon that's been locked away for millions of years. To radiocarbon, that carbon is dead, completely decayed. Mix enough of that dead carbon into a lake, and the lake's dissolved inorganic carbon ends up with a diluted radiocarbon signal. Plants that use that carbon can inherit that dilution. When you date them, they look older than they actually are. Now drop Rupia into that picture. Rupia is a submerged aquatic plant. It doesn't breathe air the way a land plant does. It pulls carbon directly from the water column. If Lake Otero's water was carrying a heavy dose of old carbon from groundwater or dissolved carbonates, then Rupia could have been building its tissues out of a mix that was already offset from the atmosphere. The seeds would still be timestamps, but they'd be timestamps on lake carbon, not necessarily on calendar years. This is the heart of the skeptical argument. Critics looked at those 21-23 plus thousand-year dates and said, maybe those aren't ancient humans? Maybe those are ordinary age humans in a chemically weird lake. Maybe the radiocarbon clock in Lake Otero was running slow. They raised a few specific points. First, basin and range geology. The region around White Sands has gypsum, carbonates, and groundwater systems that could, in principle, deliver old carbon to a closed or semi-closed basin. If you imagine a shrinking Ice Age lake fed partly by such groundwater, you can easily picture a situation where dissolved inorganic carbon is not in equilibrium with the atmosphere. Second, the magnitude of possible offsets. In some modern lakes influenced by old groundwater or carbonate dissolution, aquatic plants can appear hundreds to a couple of thousand radiocarbon years too old compared to terrestrial plants growing nearby. In extreme cases, the offset can be larger. So critics argued, if Lake Otero had a reservoir effect on the high end, then seeds that date to, say, 23,000 radiocarbon years ago might actually represent a much younger interval in calendar time, possibly nudging the humans back toward a post-Clovis or just pre-Clovis presence. Third, they noted that the White Sands team's main dated material was precisely the sort of thing that's most vulnerable: submerged aquatic plants. Not charcoal from campfires, not bones from terrestrial herbivores that ate land vegetation. Seeds from a species that lives its whole life in lake water. Taken together, the skeptics framed a very specific concern. You don't need contamination, bad lab work, or bungled stratigraphy to get misleading ages. You just need a lake whose chemistry is decoupled from the air. They weren't saying the dates are definitely wrong. They were saying, we don't yet know that they're right. So what would it take to show that a reservoir effect is actually there? One approach is modern comparison. If you have a lake today that sits in a similar geological and hydrological setting, you can sample its dissolved inorganic carbon, its aquatic plants, and nearby terrestrial plants or atmospheric CO2. You measure their radiocarbon contents and see how they line up. If the water and the aquatic plants consistently appear older than the surrounding atmosphere and land plants, you've quantified a modern reservoir offset. That doesn't prove Lake Otero had the same offset, but it shows what's plausible in that kind of system. Another powerful approach is paired dating from the same horizons in the ancient lake sediments. If, in a single layer, you can find both aquatic material, like Rupia seeds, and terrestrial material that must have drawn carbon directly from the air, like bits of land plants, charcoal, or even bones from purely terrestrial animals, then you can date both. Any consistent difference in apparent age between them is a direct measure of the reservoir effect at that time in that lake. If the Rupia seeds are, say, 1,500 radiocarbon years older than the terrestrial charcoal from the same thin layer, you can correct for that offset. If there's no significant difference, that's strong evidence that the reservoir effect was small or absent, at least for that interval. A third line of evidence is stratigraphic and regional coherence. Do the white sands ages line up with other independent climate and environmental records in the region, lake level histories, pollen records, dune activation phases that have been dated by methods not vulnerable to the same problem? If the Rupia ages correspond neatly to known cold or wet phases, and those phases are dated independently elsewhere, it supports the idea that the lake's radiocarbon clock wasn't wildly off. All of this gets at a deeper distinction that often gets blurred in public arguments, the difference between possible, plausible, and demonstrated bias. Is it possible that Lake Otero had a reservoir effect that made aquatic plants look older? Absolutely. We know such effects exist in other lakes. Is it plausible here? That depends on the specific hydrology, geology, and chemistry of this basin during the last glacial maximum. The region has the ingredients, groundwater, evaporative concentration, carbonates, to create a reservoir effect. That makes the concern reasonable, not far-fetched. But is it demonstrated? That requires actual measurements or paired dates that show a systematic offset. A theoretical risk is not the same as a documented problem. Until you see a pattern, Rupia older than terrestrial material from the same layer. By a consistent amount, you're dealing with a hypothesis about bias, not a measured correction. This is where the scientific process kicks in. You don't resolve an argument like this by declaring winners on Twitter. You resolve it by collecting more data. Other teams step in and try to replicate the work or to attack the question from a different angle. They look for alternative materials to date. Terrestrial seeds, charcoal flecks, pollen concentrates, even the carbonate coatings on certain grains, anything that might bypass the aquatic pathway. They test for modern analogues of the lake's chemistry. They build models of groundwater flow and carbon cycling. The original team responds in kind. They run additional samples. They seek out new horizons. They submit to independent labs. They invite outside groups to reanalyze their sediments. They may incorporate corrections if credible reservoir offsets are demonstrated, or they may show that such offsets are too small to rescue a late arrival timeline. In other words, the story doesn't end with the first bold claim or the first wave of criticism. The reservoir effect debate is not a reason to dismiss white sands, it's a reason to test it harder. And that's exactly what started to happen next, as other dating approaches and independent checks came into play. If you're trying to figure out whether a clock is wrong, you don't just stare harder at that one clock. You put it next to other clocks that keep time in completely different ways, and you see if they agree. That's the power of independent dating methods. They don't share the same weaknesses. They're vulnerable to different kinds of errors and biases. So when 2 or 3 fundamentally different clocks all point to the same window in time, that convergence is far more persuasive than any single technique on its own. This is where the white sand story starts to widen out from radiocarbon and Rupia seeds into a broader toolkit. One of the most important extra clocks is something with a slightly intimidating name, optically stimulated luminescence, or OSL. Strip away the jargon, and OSL is basically a light exposure stopwatch. Most mineral grains in sediment, think tiny quartz or feldspar crystals, are constantly being bombarded by low-level natural radiation from the surrounding environment. Each hit knocks electrons around, and some of those electrons get trapped in defects in the crystal lattice. Over time, more and more electrons accumulate in those traps. It's like sand slowly piling up in an hourglass you can't see. There's one big reset button: sunlight. When those grains are exposed to enough light, the trapped electrons get knocked loose. The hourglass empties. If the grains are then buried, blown into a dune, washed into a lake margin, covered by mud, they're shielded from further sunlight. The trapped electrons start accumulating again. OSL dating works by carefully sampling those buried grains, taking them into a dark lab, and then stimulating them with light in a controlled way. As the electrons are released, the grains give off a tiny amount of luminescence. Measure that glow, calibrate it against the known radiation environment, and you can estimate how long it's been since those grains last saw daylight. That age isn't the age of a plant or an animal. It's the age of the burial event, the moment when that particular layer of sediment was laid down and cut off from the surface. For white sands, that's enormously useful. The human footprints are preserved in specific track-bearing layers, thin packages of fine mud and silt, stacked between other layers deposited by the ancient lake system. If you can date the last light exposure of the grains in those very layers, you get an age estimate that has nothing to do with the lake's carbon chemistry. No dissolved carbonates, no old groundwater carbon, no reservoir effects. Just the physics of trapped electrons. The first OSL results from white sands made people sit up. When researchers dated grains from layers directly associated with the footprint horizons, the OSL ages came back squarely in the same general time frame as the radiocarbon ages on the Ruppia seeds around the last glacial maximum, roughly 21,000 to 23,000 years ago. The error bars are broader, and OSL, like any method, has its own assumptions and complexities. But the key point is that a completely different clock, sensitive to different processes, was telling a compatible story. And OSL isn't the only potential independent check in play. Carbonates in the sediments can sometimes be dated, or at least correlated to regional events. As water evaporates from a shallow lake margin, minerals like calcite can precipitate and form crusts or nodules. These carbonate features can record shifts in water chemistry and lake level. In some settings, you can date the carbonates themselves. In others, you can at least line them up with broader climate events that are independently dated elsewhere. Pollen horizons offer another line of evidence. As plants shed pollen, those microscopic grains settle into lake mud in astonishing numbers. Over thousands of years, they build up a layered record of the surrounding vegetation. Different time periods have distinct pollen fingerprints, depending on whether the region was dominated by sagebrush, grasses, conifers, or desert shrubs. If the pollen assemblages in the footprint layers match those from other regional cores that have been dated by different methods, it ties the white sands sequence into a larger, independently constrained timeline. Then there are stratigraphic markers, distinctive layers or features that can be traced across space and sometimes linked to known events. A volcanic ash layer from a distant eruption, a region-wide shift from deep-water muds to wind-blown sands indicating lake desiccation, a spike in certain minerals that signal a change in dust sources. Each of these can anchor sections of the white sands sequence to broader environmental changes that we can date using yet other methods. None of these auxiliary tools are magic. They come with their own caveats, and one of the biggest is deceptively simple, where, exactly, you sample. With OSL in particular, the method assumes those grains were fully bleached, fully reset by sunlight just before burial. If the sediment was deposited quickly underwater, or if some grains were shielded from light in turbid flows, they might carry a residual signal from earlier exposures. That would make the OSL age appear older than the true burial time. Sediment disturbance is another issue. Burrowing animals, plant roots, or later erosion and redeposition can mix grains of different ages within a single layer. If you're not careful, you might be dating a mixture rather than a clean single-event surface. Carbonates can be redissolved and reprecipitated. Pollen can be blown or washed in from older deposits. Stratigraphic markers can be eroded and redeposited in younger contexts. Every clock can be tampered with by geology if you don't understand the post-depositional history of the site. So scientists don't just ask, what does this method say? They ask, is this sample in a context where this method should work the way we think it does? When different methods agree, when Ruppia radiocarbon dates, OSL burial ages, pollen correlations, and stratigraphic markers all overlap within their respective uncertainties, that convergence doesn't prove with absolute certainty that humans were walking there at 23,000 calendar years ago. But it does make the scenario much harder to dismiss as an artifact of a single quirky lake. On the other hand, if methods diverge in systematic ways, that's a clue. If OSL keeps giving younger ages than the radiocarbon dates from the same horizon, that might signal a reservoir effect. If the pollen says younger vegetation assemblage while the OSL says older burial, you may be dealing with reworking or incomplete bleaching. Disagreement isn't just a problem, it's diagnostic. It tells you where your assumptions are breaking down and where to look more closely. This is what makes the White Sands controversy scientifically interesting, rather than simply frustrating. The debate is not a courtroom drama with a single verdict waiting at the end. It's an evolving investigation. Each new method, each new sample doesn't close the case, it reshapes it. Early radiocarbon dates open the door to a radically earlier human presence. Reservoir effect critiques forced people to interrogate that doorframe. OSL and other independent checks started to rebuild the doorway from different angles. Instead of asking, is White Sands right or wrong? A better question is, how does the weight of multiple independent lines of evidence shift as new data come in? Because while scientists were arguing about clocks and chemistry, the footprints themselves were quietly revealing something else, not just when humans were there, but how they were moving, who they were with, and what kinds of lives they were living on the shores of a dying Ice Age lake. If bones and tools are like the static snapshots of Ice Age life, the White Sands Trackways are like a flipbook. You don't just get a list of species, you get motion. Direction, speed, hesitation, overlaps that only make sense if different individuals were there at different times, walking the same patch of wet ground again and again. This is one of the first things researchers noticed when they mapped the prints over large areas. They're not looking at a single dramatic event frozen in time. They're looking at a footprint palimpsest. Some trackways cut across others at clean angles. Some are partially eroded before new prints cross them. In a few places you can see older tracks infilled by fresh sediment and then overprinted by newer ones. Lines of steps run parallel for tens or hundreds of meters, then fade out as the surface changes, while other tracks appear later, headed in the opposite direction along roughly the same corridor. If this had been one frantic escape or a single group march, you'd expect something more organized in space and time. One dominant orientation, one layer of impressions, maybe a burst of confusion at a kill site or a waterhole. Instead, White Sands looks more like a well-worn footpath. People are coming and going along the ancient shoreline and across the mudflats at different times, in different groupings. Some trackways are crisp and deep, formed when the substrate was just the right mix of wet and firm. Others are faint, their edges slumped, laid down when the mud was softer or already starting to dry. That repeating pattern, overlapping sequences in similar directions, suggests routine. Not a one-off expedition, but a landscape used and reused across seasons, maybe across years or generations. To tease more detail out of those ghostly paths, researchers turned to a surprisingly powerful set of clues: footprint size and stride. Human feet grow in fairly predictable ways. Modern pediatric data give ranges for how long a child's foot is at different ages, and how that relates to total body height. Combine that with the spacing between prints, stride length, and you can start to estimate how tall the track maker was and how fast they were moving. At White Sands, many prints cluster around sizes we'd expect for adult women and older children or adolescents, with smaller numbers that could match adult men and younger kids. That pattern, if it holds up under more analysis, might suggest that the people most often crossing this particular part of the lake margin were not random individuals, but a subset of the group, perhaps for specific tasks like gathering plants, checking traps, or moving goods. But there are big caveats. Foot size varies between populations. Soft mud can make feet spread out and look bigger. Erosion can shrink or distort impressions, and we have no guarantee that Ice Age body proportions matched those of modern reference datasets. So when you hear age and sex labels attached to specific White Sands tracks, treat them as informed guesses, not hard facts. The same goes for one of the most talked about patterns at the site, the so-called adult with child trackway. In one famous sequence, a line of larger human footprints, likely an adult of roughly modern female height, stretches for more than 1 kilometre across the ancient lakebed. Superimposed on some of those prints are smaller tracks that appear intermittently, as if a child was sometimes being carried and sometimes walking on their own. The adult's stride changes subtly along the route. In some sections, the steps are a bit shorter and asymmetrical, consistent with the extra weight and balance challenge of carrying someone. In others, the stride normalizes, and the small prints walk beside or inside the larger ones before disappearing again. It's easy to spin a story here, a caregiver hurrying across dangerous ground with a tired child, maybe under threat from predators or rival groups, or a mother making repeated trips between camp and water, juggling a toddler who keeps insisting on going down, then demanding to be picked back up. The truth is, we don't know. We don't know if they were related. We don't know their language, their kinship terms, their emotional state. The same pattern could fit mundane scenarios, routine transport of a child between gathering areas, or extraordinary ones, evacuation from a flooded camp. The footprints don't come with subtitles. What the physics of gait can tell us is more limited but more solid. The pace was generally purposeful, not meandering. The adult was moving steadily in one direction, with only minor deviations. Speed estimates based on stride and footprint depth suggest a brisk walk, not a slow stroll, with a few segments where pace seems to pick up, perhaps on slightly firmer ground or in response to some unseen stimulus. Elsewhere at White Sands, other human trackways paint different movement styles. Some are almost arrow straight, the kind you'd expect from someone who knows exactly where they're going and is focused on getting there. Others show zigzags, pauses and turns, as if the person was scanning the ground, picking up objects or following something unpredictable. In a few places, overlapping prints with varied orientations and speeds hint at small gatherings, maybe multiple people converging on a shoreline patch rich with resources, then dispersing again. But it's important not to overread these little knots as villages or crowds. Trackways record individuals, not head counts. If 10 people cross a surface in single file over a few days, you might only see one reinforced line of prints. That's one of the sharp limits of this kind of evidence. From footprints alone, we can't recover spoken language, myths, clan structures, or group size with any precision. We can't tell whether these people thought of this lake as home or just one stop on a much longer seasonal circuit. We can infer that at least one adult sometimes carried at least one child. We can't say whether that child grew up to have kids of their own along this same shoreline. What we do get, and what makes white sand so unusual, is a behavioural snapshot at a resolution we almost never see in Ice Age archaeology. Most of the time, the record of Pleistocene humans comes in big blurred chunks, a scatter of stone tools accumulated over centuries, a butchered mammoth with a jumble of cut-marked bones, a cave floor layered with ash from hundreds of fires. You know people were there, you know what they could do. You rarely catch them in the act. Footprints flip that. For a handful of moments you see a person deciding where to put each footfall. You see them speed up or slow down. You see where they hesitated at the water's edge, where they cut across a mammoth path, where they shared the same mud with giant ground sloths and dire wolves. Those choices are the closest thing we have to watching Pleistocene humans move in real time. And once you start setting those human paths against the animal trackways crisscrossing the same surfaces, the picture gets even richer. Because humans weren't walking alone on the shores of Lake Otero. They were moving through a crowded, dangerous neighbourhood of Ice Age megafauna. When researchers first started mapping the wider area around the human tracks, they realised something striking. This wasn't just a human corridor. It was a whole Pleistocene neighbourhood stamped into the mud. The most obvious neighbours are the mammoths. Their tracks are huge, dinner-table-sized depressions with a regular, almost ponderous rhythm. Lines of these prints parallel the old shoreline, sometimes veering toward what would have been shallower water, sometimes looping back. In places, mammoth paths and human paths run roughly side by side, offset in time, but sharing the same preferred ground, firm, not too boggy, close to water with a good line of sight. Elsewhere, you get a very different kind of track maker, giant ground sloths. These animals weren't just oversized tree sloths, they were tank-sized herbivores with massive claws, walking on the sides of their feet. Their footprints at white sands show a distinctive kidney bean shape and a wider, rolling gait. In some sequences you can see them moving slowly across the mudflats, detouring around deeper patches, sometimes stopping and pivoting as if they were rearing up to feed or sniff the air. Add in trackways from ancient camels, bison, proboscideans of different ages, and what look like canid and possibly big cat prints, and the lake margin starts to feel less like a quiet backwater and more like the main road through a busy Ice Age ecosystem. The key is how these tracks overlap and intersect. You don't have mammoth footprints on one buried surface, and human prints a metre above them, separated by centuries. In many cases they're on the same walking horizon, crossing and recrossing each other. A sloth track is partially slumped. Then a set of human prints crosses its edge. In another patch, the sequence reverses. Human prints start to blur with drying. Then a mammoth steps through the softened impressions. This stacking of tiny events tells us a few important things without having to stretch the evidence. First, humans and megafauna weren't just using the same general region in some abstract sense. They were using the same specific spaces, the same shoreline arcs, the same mudflats, close enough in time that their tracks could overprint one another before erosion wiped the slate clean. Second, those surfaces must have remained attractive for a while. You don't get that much overprinting if the lake is flashing between full and bone dry every few days, or if the mud crust is scoured away by storms after every visit. The persistence of walkable, re-wettable ground suggests a relatively stable phase in the lake's cycle, water near the surface, repeated wetting from waves or rain, but not constant flooding. That, in turn, says something about the environment. Lake Otero in this period was not a barren salt flat. It was a productive wetland oasis in an otherwise arid landscape. The mammals tell you that. Mammoths and ground sloths are big-bodied herbivores. They need serious biomass, grasses, sedges, shrubs, whatever grew along those shorelines and in the surrounding basin. Camels and bison reinforce the picture of open habitats with patches of denser vegetation. If you think in terms of seasons, the track patterns hint at certain windows when conditions were best. Some horizons are dominated by heavy mammoth and sloth use, with relatively few human prints. Others show more human traffic cutting across older animal tracks that could reflect seasonal shifts, herds favouring the lake during particular parts of the year when other water sources dried up, humans timing their movements to coincide with those predictable concentrations of game and plant resources. Now layer in behaviour. At White Sands, there are a few trackways that have drawn special attention because they may preserve interactions, or at least reactions, between humans and megafauna. One much discussed surface shows a giant ground sloth path intersected by human prints that seem to circle around it. The sloth's gait, based on footprint spacing and orientation, changes near the human tracks, from straightforward plodding to a kind of stop and pivot pattern, as if the animal was turning repeatedly, maybe standing up on its hind limbs. It's tempting to see this as stalking or harassment, people deliberately approaching the sloth, forcing it to turn and face them, testing its reactions or trying to drive it. You can spin scenarios of hunting parties probing a dangerous animal from multiple angles. It might be that. It might also be curiosity, or simple coincidence on a slippery surface, where changes in footing force changes in gait. The prints don't come with arrows and captions. Predator-prey dynamics can also show up in how animals use space relative to one another. If you map enough trackways, patterns emerge. Herd animals tend to converge on particular approach routes to water, creating dense traffic lanes. Potential predators or cautious humans might skirt the edges of those lanes, placing their own trackways off to one side, where visibility is good, but you're not caught in the middle of a crowded approach. Some of the human paths at White Sands do exactly that. They edge along the margins of heavy mammoth use areas instead of cutting straight through them. That could be energy-efficient route finding over firmer ground. It could also reflect a kind of cautious coexistence, sharing a resource zone with massive animals while minimizing close encounters. On the carnivore side, canid or large felid prints that follow behind herbivore paths, or that fan out near access points to the lake, might indicate ambush behavior or scavenging. Humans moving through the same mosaic would have had to factor that into their decisions. A shoreline rich in mammoth dung and trampled sedges was also a place where big, hungry predators might linger. All of this ecological detail matters for thinking about early human dispersal. People didn't spread into North America as abstract dots on a map. They moved along real resource networks. A lake system that could support mammoths, ground sloths, camels, and bison in the middle of the last glacial period was a natural hub, reliable water, plant foods and opportunities for hunting or scavenging all bundled together. Following megafauna herds along their seasonal circuits would have been one logical way for humans to explore new territory. At the same time, the sheer size and danger of those animals imposed limits. You can't camp just anywhere on a shore where multi-ton herbivores and their predators come to drink. You need safe vantage points, escape routes and strategies for staying out of the wrong trackway at the wrong time. The White Sands footprint record drops us into that balancing act. We see humans and megafauna sharing ground within short windows of time. We see hints of avoidance, possible approach, maybe even harassment. We see a wetland landscape that was both a lifeline and a risk zone. What we do not see, and this is crucial, is direct, unambiguous proof of kills, butchery, or close quarters confrontations between humans and specific animals on these exact surfaces. Overlapping tracks can tell us about shared habitat and relative timing. They can't, by themselves, prove who hunted whom, or whether a particular sloth died because of those circling human footsteps. To bridge that gap, you'd need cut-marked bones, embedded stone points, patterned carcass processing sites, the kinds of evidence archaeologists look for elsewhere in the Americas. At White Sands, the footprints provide the stage directions and some of the choreography. The blood and bone part of the story, if it's there, is still mostly off-stage. Even so, the megafauna context transforms how we read the human trails. Those adults and children weren't just walking across anonymous mud. They were threading their way through a living, dangerous Ice Age community, watching mammoth herds, skirting sloth paths, keeping an eye out for predators, and making choices shaped by all of that. To understand what those choices might have looked like day to day, we have to zoom in even further on the human side of the equation, how they moved, what they carried, and how they navigated this loaded landscape. When you zoom in on individual human trackways at White Sands, they stop looking like anonymous dots on a dispersal map and start looking like pieces of somebody's day. One of the first things researchers look at is gait. How long each step is, how much it varies, how the feet are rotated. A steady, regular stride with evenly spaced prints usually means someone walking at a comfortable, sustainable pace. At White Sands, plenty of adult trackways fit that pattern, medium stride lengths, modest toe push-off, no big slips. That's what you'd expect from people moving along a familiar path, not sprinting from danger or staggering with exhaustion. But then you get sequences where the stride lengthens, the heel-to-toe impression deepens, and the prints space out more. That's the signature of someone speeding up. Maybe they're hurrying to catch up with others, maybe they're racing a storm front, maybe they're just moving quickly across a soggy patch to get back onto firmer crust. You can't always tell why the pace changed, but the fact that it did tells you effort and decision were involved. This wasn't a uniform trudge, it was stop-and-go movement, adjusting speed as conditions changed. Stride variability can also hint at fatigue or awkward loads. A tired walker tends to shorten their steps, wobble a bit, and push off less forcefully. Some trackways show that pattern intensifying over distance. The early prints are crisp and regular, later ones a little more shuffly, with more lateral spread. That could be age, an older person with less stable balance, but it could also be someone who's been on their feet for hours, carrying something heavy, trying not to slip on saturated mud. That brings us to what might be one of the most evocative sets of prints at White Sands, the possible carrying trackways. On one long trackway that's been studied in detail, an adult walks several kilometres along the ancient lakeshore and back again. In one direction, the footprints are wider, a bit messier, with more slip and twist. The centre of pressure, the part of the foot that bites hardest into the mud, shifts slightly, as if the person's mass is off-centre. In the return leg, the same individual appears to be walking lighter and more balanced. One interpretation is that they were carrying a child or a substantial load one way, then coming back unburdened. In some sections there are small prints that seem to peel off and rejoin the main trackway, as if a kid was sometimes being carried, sometimes walking beside the adult. The adult's stride shortens where the small feet appear, as though matching pace with shorter legs. Is that certain? No. Alternative explanations exist. Differences in substrate, wind-driven drying of the surface, subtle changes in walking angle. But the pattern is consistent with what biomechanics studies tell us about how humans walk when they're loaded. We lean, our lateral stability drops, our steps become more variable, our footprints record that extra sway and force. Now think about why you carry a child across a particular stretch. Maybe the mud is deeper and a toddler would bog down. Maybe you've entered an area you think is risky, closer to where mammoths churn the shore, or where predators might lurk, and you want that kid in your arms, not lagging 20 meters behind. Maybe you're moving quickly to or from a focal point, a carcass, a good stand of edible plants, a water pocket you know is still fresh. Here the shoreline itself becomes part of the story. Lake margins are resource magnets. In Ice Age basins like Otero, they functioned as what some archaeologists call linear oases, elongated strips where water, plants and animals concentrate. For mobile hunter-gatherers, these are natural highways. You don't bushwhack straight across every dune and dry playa. You hook onto the feature that reliably gives you what you need: drinkable water, digging sites for roots and tubers, shellfish or snails, stands of reeds, and the tracks of whatever game you're following. The white sand's footprint corridors track along the old shorelines. Humans aren't randomly crisscrossing the basin. They're moving parallel to the lake edge, much like the mammoths. That suggests deliberate route finding, follow the curve of the water, stay on firm but moist substrate, keep visual access to both the lake and the open ground behind you. Along such a highway, different members of a group may be doing different jobs. Some trackways hint at scouting behaviour. You see a single set of prints branching away from a main traffic line, angling toward zones with fewer heavy animal tracks, or toward what would have been inlets and coves. The person goes out, loops, and then either returns along the same path or rejoins a parallel route. That looks a lot like someone checking a side channel. Is the water still there? Are there fresh tracks from something worth hunting, or something you want to avoid? Other sequences show repeated use of the exact same microroute. Multiple human trackways, separated in time, cut down the same narrow swath of shoreline. That could be simple topography. That strip was just the best walking surface. But repeated, near identical paths also suggest mental maps. People remembered, this is the way we go around that boggy patch, or this is the safest line past where the sloths tend to cross. If a group is using the lake on a regular basis, you can start to imagine a whole logistics chain. Maybe a small party goes ahead at dawn to scout water levels and animal sign, marking a safe crossing point, or identifying a strand of shoreline that's less churned by mammoth feet. Later, others follow with children and loads, taking the route the scouts picked out. On the way back, one adult carries a tired kid, while another walks unencumbered, leaving two slightly different adult trackways side by side. Overlay, overload, overload, overlay, overload, overlay, overload, 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 overload. Lake Otero wasn't a static, bathtub, full body of water. It expanded and shrank with climate pulses, with inflow from rivers, with evaporation. The track record suggests phases where shorelines were fairly stable for long enough to accumulate multiple walkways, but even within those phases, humans would have had to deal with shifting sandbars, new inlets, and occasional storm surges that re-wetted and destabilized the mudflats. Where you choose to walk is a risk calculation. Too close to the water line, and you could hit unexpectedly soft ground, risking a fall or losing a load. Too far back into the dunes, and you lose quick access to water and plant resources, and maybe put yourself in more exposed terrain where predators can approach unseen along gullies. Given that this was a landscape used by enormous, sometimes unpredictable animals, you're also thinking about escape routes, open zones where you can step upslope if a mammoth herd swings your way, or where you can get out of the path of a panicked ground sloth. Footprints can't tell us what people were thinking as they made those decisions. But they do show the outcomes: a preference for certain elevations, avoidance of particular boggy hollows, convergence on slightly raised, firmer benches. They show points where someone turned back instead of pressing into deeper tracks. They show speed-ups and slowdowns that might map onto perceived danger or relief. It's important to keep the boundaries clear here. From the prints alone, we can measure pace, direction, spacing, and relative timing. With experimental data on human gait, we can make grounded inferences about walking speed, load carriage, and substrate conditions. With ecological context, we can sketch plausible reasons why people favoured some routes and not others. What we cannot do with high confidence is reconstruct inner narratives. This person was afraid. That person was hunting. This was a ritual procession. Those stories may be tempting, but they go beyond what the evidence can bear. Still, compared to stone tools or scattered bones, footprints add something almost no other kind of evidence can: texture. They capture the wobble of a tired leg, the shorter stride of someone matching pace with a child, the sudden lengthening of steps across a treacherous patch, the branching of a scout's detour off the main path. They show humans not just as carriers of a technology or a genetic lineage, but as bodies in motion, making small, moment-to-moment decisions in a risky, resource-rich landscape. From those faint impressions in ancient mud, we glimpse mobility as a lived experience, not a single great migration arrow sweeping across a map, but countless careful choices about where to place the next foot. If people were moving along these shorelines, carrying kids, scouting side inlets, making all these small decisions we can see in the tracks, where's everything else? Where are the camps, the burned bones, the trash heaps of broken stone tools? This is one of the first objections that comes up when you tell someone there are human footprints in New Mexico from around 21,000, 23,000 years ago. If humans were really here that early, the argument goes, shouldn't the basin be full of their stuff? Not necessarily. Start with what a footprint actually represents. A moment. A few seconds, maybe a few minutes, in which a person's bare or lightly shod foot pressed into soft mud. The water content was just right, the print dried enough to hold its form, and then it got buried quickly by fresh sediment. All of those conditions have to line up for a trackway to survive. A campsite is different. It's not one magical set of conditions. It's a messy accumulation. Fire, trampling, wind, scavengers, weathering. Artifacts get moved, broken, dispersed. And critically, they don't need the same preservation sweet spot that footprints do. So they follow a different taphonomic path. At White Sands, the thing that's perfect for footprints is exactly what's terrible for preserving open-air camps. You've got a fluctuating lake that lays down fine, wet sediments along its shore. Then, as water levels drop and climate shifts, those flats get exposed, dried, crusted, and finally overrun by migrating dunes. Sand scours the surface, abrades it, reworks it. New dunes roll in, old ones blow out. Whole packages of sediment get inverted, truncated, or eroded away. If you pitched a small short-term camp up on a slightly higher, drier bench above the mud flats, the evidence wouldn't look like some big, dense village. It would be a handful of flakes from sharpening a point, some ash from a small fire, maybe a broken tool or two, and bones that animals have chewed and scattered. Then picture thousands of years of dunes crawling over that spot, ripping off the top few centimetres, redepositing them somewhere else, or burying them metres down. The footprint horizons we're seeing are essentially exposed snapshots, where the lake margin mud got sealed, then re-exposed as the dunes migrated. The odds that the exact same processes would also perfectly preserve and then reveal a delicate scatter of tools from a nearby camp are much lower. So what would we reasonably expect to find if we could sample the right places deeply and systematically? Not a Clovis-style kill site with spear points sticking out of mammoth ribs. These were likely highly mobile foragers visiting the shoreline as part of a larger seasonal round. Think ephemeral use, day trips, short stays, activity-specific spots. That kind of land use leaves light material signatures, what archaeologists call very low-density scatters. A few microflakes from resharpening a blade, maybe a simple flake tool made on a random pebble. Hearths that are just thin, diffuse lenses of charcoal and reddened sediment, almost invisible without careful excavation and lab work. Bone fragments so small and weathered you'd miss them, unless you screen sediments very finely. And we may already be brushing up against the limits of what's even recoverable. Wind and water can concentrate or disperse artifacts. Buried hearths can be sliced off by later erosion, leaving only a ghostly chemical signal. Slightly elevated phosphates trace magnetic enhancement from heating. Once that signal is a metre or two down under active dunes, you're not going to see it from the surface. You need coring, trenching, geophysics, slow targeted work. This pattern, clear behaviour, minimal stuff, isn't unique to white sands. Around the world, track sites often show us animals and humans passing through landscapes that otherwise look archaeologically empty. In East Africa, there are Pleistocene footprints of people and ungulates preserved in lake margin mud, with no dense stone tool scatters right beside them. In Italy, ancient human trackways run across volcanic ash, flows with almost nothing in the way of artifacts. Even the famous Laetoli footprints in Tanzania, made by hominins over 3.5 million years ago, aren't anchored to a big living site full of tools and bones. They're a route, not a camp. That's because walking behaviour and residential behaviour don't overlap perfectly. You don't nap stone tools in the middle of the boggiest mud. You don't butcher a carcass right at the waterline if you can help it, where scavengers and trampling animals churn everything up. You step through, get what you need, and retreat to slightly safer, firmer ground, often in a different microenvironment that may not preserve footprints at all. Then there's the simple fact of survey limits. White sands is huge. The portions of the ancient lakebed we've mapped intensively are still a tiny fraction of the total. Most work has understandably focused where prints are eroding out, because they're dramatic, fragile, and time-sensitive. Systematic subsurface survey for subtle campsites, micro-debitage fields, or buried hearths is only just beginning. Future work might use fine-grained sampling to look for microscopic stone chips, invisible to the naked eye, or geochemical signatures of burning buried under dune sands. Ground-penetrating radar and other geophysical tools could pick up buried surfaces with repeated burning or trampling. Sediment cores could reveal thin, charcoal-rich layers that never make it to an excavation trench unless you know exactly where to dig. It's entirely possible that as methods tighten and coverage expands, we'll start to see more of the quiet archaeology that goes with the noisy footprint record. A stray flake here, a tiny hearth there, residues trapped in former wetland soils. But even if that never happens, even if White Sands never produces a big, glamorous toolkit assemblage, the site is still extraordinary. Stone tools tell us that at some point in a broad time window, someone capable of making a particular technology was in a region. Footprints tell us that on a specific day, at a specific hour, actual individuals walked here at this speed in this direction, sometimes side by side, sometimes carrying a child. They give us resolution, not just presence. So when we ask, where are the tools, it's worth flipping the question around. Maybe at White Sands, the tools are ancillary. Maybe the main artifact is the landscape-scale record of movement itself, the corridors of steps locked into ancient mud, showing that by the height of the last ice age, humans weren't just appearing in North America. They were already at home enough to be leaving only their footprints behind. To understand what those footprints really mean, we have to zoom the map way out. New Mexico, 21,000 plus years ago, is just one tile in a much bigger puzzle. how humans even got into the Americas in the first place. For most of the 20th century, the story sounded clean and simple. During the last ice age, sea levels dropped more than 100 meters. That exposed a land bridge between Siberia and Alaska called Beringia, a broad, cold, but surprisingly productive steppe stretching for hundreds of miles. At some point late in the game, maybe around 16,000 years ago, people walked across that bridge from Northeast Asia into what's now Alaska. Then, as the great ice sheets covering Canada began to retreat, a gap supposedly opened between them, a long deglaciated corridor running down through the interior of the continent. According to the classic model, those first Americans followed that ice-free highway south, hunting big game, spreading rapidly, and eventually giving rise to the Clovis culture we see all over North America by about 13,000 years ago. Neat, linear, easy to teach in a textbook, and almost certainly too simple. Even before White Sands, that timeline was under pressure. Geological work on the ice-free corridor showed that while bits of it may have been deglaciating earlier, it probably didn't become a continuous, biologically viable route, with plants, animals and usable landscapes until somewhere around 14,000, 15,000 years ago. In other words, if humans came through that interior passage, they arrive in mid-continent just in time to explain late Pleistocene sites, but not anything earlier. Drop White Sands into that picture with dates pushing back toward 21,000, 23,000 years ago, and the problem gets much sharper. If people were walking around southern New Mexico at the height of the last glacial maximum, then one of two things has to be true. Either they got into the Americas long before the corridor was open, by some other route, or our understanding of the timing and nature of that corridor is wildly wrong, and it was traversable far earlier than most current reconstructions allow. Most researchers lean toward the first option, because there's another pathway that has been gaining ground for decades: the coast. Imagine the same lowered sea levels, but instead of focusing on a single bridge in the middle, trace your finger along the edge of the continent, from Japan and the Russian Far East, along the Kuril Islands, down the coast of Kamchatka, across Beringia's southern rim, and then along the Pacific shore of Alaska and British Columbia, a kind of kelp forest highway, rich in fish, shellfish, marine mammals, birds, and seaweed. If humans had already developed decent boats, nothing spectacular, just seaworthy enough for near-shore travel and short crossings, they wouldn't need a giant continental highway through the ice. They could hug the coastline, exploiting marine resources, slipping past glaciated interior regions by moving along ice-free refugia on the outer shelf and scattered pockets of habitable land. The coastal route has a lot going for it. It doesn't require a fully deglaciated interior. It fits with evidence that people were in southern Chile, the Monte Verde site, by at least 14,500 years ago, which is very hard to reconcile with a late opening ice corridor and a slow trickle south. And it matches what we know about humans elsewhere. Maritime abilities show up early and often. People were crossing deep water to reach Australia more than 40,000 years ago. There's nothing inherently implausible about coastal travel in the North Pacific by 20,000 years ago. So why don't we have a neat chain of coastal camps running from Kamchatka to California? Because most of that ancient coastline is gone. With sea levels over 100 meters lower, the productive shelf environments people would have favored are now underwater, sometimes tens of kilometers offshore. Any early shoreline sites, middens and camps that did exist are drowned, buried under marine sediments, scoured by waves, or masked by later coastal reshaping. We're asking archaeology to find evidence in a landscape that's literally been erased and rebuilt. Underwater archaeology is improving, and there are tantalizing hints: submerged landforms, isolated finds, but nothing like the dense record we'd need to map a continuous migration. The absence of a perfect trail here says more about preservation and access than it does about what people were capable of. Then there's Beringia itself, not just as a bridge but as a home. Genetic studies over the last 2 decades have suggested something called the Beringian standstill, or Beringian pause, when researchers model the divergence of Native American lineages from their closest relatives in Northeast Asia. They see a pattern that fits a scenario like this. A founding population leaves mainland Asia, maybe 25,000, 30,000 years ago, reaches the Beringian region, and then stays. Not for a couple of generations, but potentially for thousands of years, isolated enough to accumulate distinctive genetic signatures, but not cut off from the resources needed to survive. Think of a relatively stable, cold but livable refugium at the edge of the world. Only later, maybe sometime after 20,000 years ago, as ice margins shift and windows open, do descendants of that standstill population move into the rest of the Americas, probably by multiple routes, some along the coast, some eventually through interior passages when they become viable. If that's roughly right, then White Sands stops looking like a weird isolated outlier and starts looking like a very early southern footprint, literally, of a population that had already been on the American side of Beringia for quite a while. But one site, no matter how dramatic, is not a migration map. Those trackways in New Mexico tell us that humans were present in interior North America by around 21,000, 23,000 years ago. They do not by themselves tell us whether those people's ancestors came strictly along the Pacific coast, threaded an early patchy interior corridor, or arrived via some combination of routes over thousands of years. What they do is change the kinds of questions and predictions we can make. If people were this far south this early, then we should expect older or contemporaneous traces in Alaska and Western Canada, especially in places that would have been ice-free pockets or coastal refugia. Submerged sites on the drowned continental shelf off Alaska and British Columbia, preserved in spots where erosion has been gentle and sedimentation steady. Sparse but detectable interior evidence in the northern Rockies and Great Basin, tiny scatters of tools, butchered bones or modified plant, remains in context older than 16,000 years. And more footprint sites. Ancient lake margins, wetlands and river flats across the western interior become high-value targets, places where even a brief visit could leave a preserved trackway. Anywhere there was fine sediment, fluctuating water levels, and later burial, playa basins, old deltas, spring-fed marshes, suddenly moves to the top of the list. White Sands doesn't answer the "how did they get here?" question. It sharpens it, forces it to reckon with a deeper timeline, and points us toward the kinds of places, coastal shelves, Beringian refugia, drowned shorelines, hidden wetlands, where the next critical pieces of the story are likely waiting, still buried, just out of sight. White Sands didn't explode into a vacuum. Archaeologists had been poking holes in the old nothing before Clovis timeline for decades. The problem was never evidence in the absolute sense. It was the kind of evidence, and how clean the story around it was. Take Monteverde in southern Chile. That site became the poster child for pre-Clovis, not because it was the first claim, but because it was the first one that survived a really brutal level of scrutiny. At Monteverde you get a whole package: wooden structures, preserved plant remains, bits of hide, stone tools, even possible medicinal plants. The site sits in a waterlogged valley where organic material got sealed in anaerobic mud. Another perfect preservation trap, just a different flavour from White Sands. Multiple dating methods converge around at least 14,500 years ago, maybe a little earlier. The context is tight. Artefacts in place, features still recognisable, sediments that make geological sense. That combination, artefacts, features and credible dates in a coherent setting, is what eventually forced almost everyone to admit, okay, humans were in South America before Clovis. But Monteverde isn't alone. Far to the north, there's bluefish caves in the Yukon. For years, the claim there has been that some animal bones show cut marks made by stone tools, with dates pushing back toward 24,000 years ago. If that holds, it would mean people were butchering animals on the American side of Beringia during the last glacial maximum. The controversy is all about context and interpretation. The bones come from a complex cave deposit that formed over a long time, with material getting moved around. Distinguishing ancient human cut marks from carnivore tooth marks or modern damage is hard, and the number of convincing specimens is small. Some researchers are persuaded, others argue the sample size is too thin and the taphonomy too messy to hang a big migration story on. Then you have Galt and Buttermilk Creek in Texas. These are rich sites with deep stratigraphy, layer cake deposits with Clovis material on top, and older stone tools below. At Buttermilk Creek, archaeologists argue that the pre-Clovis layer, around 15,500 years old, contains a whole technological tradition, hundreds of artifacts, production debris, and tool types that look like plausible ancestors to later Clovis points. Critics don't necessarily deny that the tools are old. They question whether the layers are as sealed as they appear. Could later artifacts have been pushed down by animal burrows, root action, or cracking sediments? Are the dating samples really tied to the layer with the tools, or to pockets of older or younger material sneaking through? Meadowcroft Rock Shelter in Pennsylvania runs into similar issues. It's a deep shelter with claims of human occupation going back perhaps 16,000, even 19,000 years. Stone tools, hearths, plant remains, it's all there. But questions about possible contamination of radiocarbon samples and tricky geological processes have kept Meadowcroft in a sort of limbo, suggestive, important, but not quite the smoking gun that forces everyone to rewrite intro textbooks overnight. And there are more. Cactus Hill in Virginia, Cooper's Ferry in Idaho, a growing list of sites that hint at people earlier than the classic Clovis window. Each has something going for it, tools, bones, hearths, stratigraphy, and each has something that makes part of the community wince. Ambiguous marks, complicated deposits, thin sample sizes, or dating that leans heavily on one method. This is why the debate has dragged on. It's not that archaeologists are stubbornly refusing to see obvious evidence. It's that the record they work with is inherently messy. Sediments move, roots grow, rodents dig, rivers flood. Fires burn and reburn the same spot over centuries. All of that can blur or scramble the neat association between this artifact, this layer, and this date that you'd love to have. White Sands drops into that landscape of contested hints with something very different, direct traces of walking humans. Nobody is arguing that the White Sands tracks were made by mammoths, giant sloths, or some weird erosion pattern. The shapes are human, the biomechanics are human, their patterns of pace and stride and overlap line up with how modern people move. In a sense, the what is the least controversial part of the site. The debate shifts instead to the when and the how solid is your clock. Are the seeds truly the same age as the footprints? Could old carbon have snuck into the lake system and made young things look ancient? Are the stratigraphic relationships as simple as they appear, or did groundwater, burrowing, or subtle erosion shuffle the deck? That makes White Sands the mirror image of places like Bluefish Caves or Galt. There the human signal rests on interpreting artifacts or marks that might be ambiguous, but the dating context is often more straightforward. At White Sands the human signal is brutally clear, bare feet on wet ground, but the dating context is what everyone wants to test and retest. And this is where the bigger pattern starts to matter. If Monteverde points to people in Chile by 14,500 years ago, And sites like Galt, Cooper's Ferry, and Meadowcroft hint at people in North America before 13,000 years ago, and White Sands really does anchor humans in New Mexico past 20,000 years ago. Those lines begin to converge on a single conclusion. Humans were in the Americas earlier and more widely than the old Clovis-first model allows. None of these lines is perfect on its own. Each has caveats, uncertainties, and critics. But science doesn't usually wait for a single flawless data point. It moves when enough imperfect but independent pieces start pointing in the same direction. Think of it like triangulation. One reading from one faulty instrument might be noise. 3 different instruments, all with their own quirks, all converging on roughly the same answer that starts to look like signal. That's also why it's dangerous to treat White Sands or any one site as the proof. If you hinge the entire narrative about early Americans on a single trackway or a single cave, you set the whole story up to collapse if new data revises the dates or the interpretation. Archaeologists would much rather have a network, a patchwork of footprint sites, cave deposits, open-air camps, butchered bones, and submerged coastal sites, all roughly consistent with each other, all filling in different parts of the timeline and map. In archaeology, a consensus shift almost never happens because of one discovery, no matter how dramatic. It happens like this. First, a few outlier sites start causing discomfort with the dominant model. They're argued over, doubted, partially accepted. Then, more data arrives from new digs, better dates, different regions, even from genetics or paleoecology, and some of those outliers start to look less like mistakes and more like early glimpses of a new pattern. Eventually, textbooks get updated, students start learning the revised story as if it had always been obvious, and the old model survives only in outdated charts and nostalgic arguments. White Sands is sitting right in that uncomfortable middle phase. It's not the first pre-Clovis claim, and it won't be the last. But by offering a vivid, unmistakably human signal at an exceptionally early date, it's putting fresh pressure on the timeline and forcing every other candidate site to be reconsidered in a new light. If the dates hold and if more early sites join it on land, in caves and under the sea, then those footprints in New Mexico won't be the proof of anything. They'll just be one set of tracks in a growing trail that shows humans had been here, adapting and exploring long before the ice sheets fully loosened their grip. If you zoom out from the mud and the mammoths for a second, White Sands is also a perfect case study in how science actually works when the stakes are high and the claim is big. On paper it sounds simple. Researchers find something surprising. They write a paper. Other experts check it. If it passes, boom, new knowledge. But in practice, especially in fields like geoarchaeology, that process is less like a neat relay race and more like a long courtroom trial with a rotating cast of skeptical lawyers. The first White Sands papers didn't stroll into the literature unchallenged. They went through peer review, which is basically the first filter. A few specialists read the methods, poke holes, ask for clarifications, maybe demand more data. Only when the authors have patched as many leaks as they can does the work get published. That's not the end. It's the beginning. Publication doesn't mean we now know this is true. It really means these methods and interpretations are solid enough that the rest of the community should start testing them. Every big claim comes with an invisible label, provisional. That's where critique and follow-up studies come in. Critique in science isn't a personal attack. It's a stress test. With White Sands, skeptics immediately went after the weakest link, the dating. Are the seeds really the same age as the prints? Could old groundwater carbon make them look ancient? Could burrows or cracks have moved younger or older material around? Those aren't nitpicks. They're exactly the questions you'd want people to ask if you care about getting the story right. So other teams step in. They retest the same layers with different labs. They use different kinds of dating, like optically stimulated luminescence on the sediments themselves, instead of just radiocarbon on seeds. They look for independent markers in the lake record, volcanic ash layers, shifts in pollen, changes in lake chemistry that should line up in time if the picture is coherent. That's what replication looks like in geoarchaeology. You're not recreating the footprints, you're recreating the reasoning. New samples, new labs, new methods, sometimes new field seasons that re-expose the same trackways and sample them again from scratch. The goal is to see whether the early dates survive when you change as many variables as you reasonably can. Along the way, researchers also build and attack alternative explanations. Old carbon made these look too ancient is an alternative hypothesis. So is the seeds got reworked from older sediments, or the prints are younger than the dated material above and below because of some weird erosion event. You don't just say, well, that seems unlikely. You test those scenarios against everything else you know. If there was a big reservoir effect from old carbon, you'd expect it to show up in other lake records nearby, in other organic materials from the same system, not just in one narrow band of seeds. If burrowing or cracking had scrambled the layers, you'd expect messy, discontinuous stratigraphy, disturbed bedding, pockets of mixed material, not pristine, parallel lamination with tracks cutting across it in logical sequences. Each what if has geological and chemical fingerprints. The more you look for them and don't find them, the more confidence you gain that the straightforward reading might actually be the right one. None of this unfolds the way media headlines make it look. When the first White Sands paper dropped, many outlets went with some version of humans were in America 23,000 years ago. Everything you learned is wrong. It's punchy. It gets clicks, but it also quietly scrapes off all the nuance. A couple of years later, when critiques appeared, a new wave of headlines announced, "Controversial footprints may not be so old after all," or "New study casts doubt on earliest Americans' claim." If you only follow the headlines, it feels like science is constantly reversing itself. First it was certain, then it was wrong. Now who knows? But that apparent flip-flopping is more about storytelling than about the underlying process. Inside the papers, scientists almost never say proves. They use phrases like consistent with, supports, suggests, is compatible with. Those words aren't weasel terms. They're carefully calibrated signals about confidence. Consistent with means, if our hypothesis is true, this is exactly the kind of evidence we'd expect, but it could also fit other explanations. Supports is a step stronger. The data actively make the hypothesis more likely than some competitors. Suggests usually means the pattern is there, but the sample size is small, the method is new, or alternative explanations haven't been fully beaten down yet. Proves, in contrast, is almost never used in serious discussion, because in messy, ancient systems, absolute proof is a fantasy. You're always dealing in probabilities, not courtroom-style beyond a reasonable doubt, but beyond a reasonable pile of alternative geologic nightmares. With White Sands, the language has shifted incrementally over time. Early critics argued that the dates could be affected by reservoir effects. Follow-up work that used different materials and methods reported ages that were broadly consistent with the original claims. That doesn't mean the story is frozen forever. It means the early arrival interpretation has survived several rounds of stress testing and, at least for now, is the best explanation that fits all the data on the table. If that changes, if a new method or core or site forces a major rethink, that's not failure. That's the system doing what it's supposed to do. The temptation, especially in big, emotionally charged questions like who was here first, is to demand closure. We want a final answer, an official date, a map that won't change. But the real power of science lies in its willingness to live with uncertainty while still making progress. Uncertainty isn't a bug, it's the engine. It's the gap between what we know and what we want to know that drives new surveys, new techniques, new arguments. White Sands sits right in that gap. The tracks are real. The people were there. The exact timing, the routes they took, how they fit into the broader peopling of the Americas, that's the part still sharpening into focus. If you can learn to read the confidence language, to see critique as refinement instead of attack, and to treat shifting interpretations as signs of a living field instead of chaos, then sites like White Sands stop being gotchas and start being what they really are, invitations to keep looking. And that matters, because even footprints don't last forever. Most of what our ancestors did vanished without a trace. Every camp they set up, every argument they had, every story they told by firelight gone. So when we find something as intimate as a footprint, it feels weirdly solid, like the past has finally left a clear message. But that solidity is an illusion. Footprints live on a knife edge between preservation and destruction. White Sands only exists because a whole chain of unlikely events lined up, over and over, across thousands of years. Start at the beginning with a single step. You've got a saturated surface, fine mud or soft wet sand at the edge of an Ice Age lake. Not too dry, or your foot won't sink in, not too soupy, or the edges will collapse and slump. The grains need just enough cohesion that when your heel hits and your toes push off, the surface deforms and holds the shape. Then it has to dry just right. If it dries too fast in blazing sun and wind, the print's crust can curl and flake away. If it dries too slowly, or gets re-wet by waves or rain, the details blur into mush. The perfect scenario is almost Goldilocks. The imprint firms up, the water level drops a little, and the surface becomes stiff enough to keep its geometry, but still soft enough that it can be moulded again by the weight of passing animals. Next, burial. To fossilize a footprint, you need it covered quickly by a new layer, a thin sheet of silt from a flood, a dusting of volcanic ash, a wind-blown blanket of fine sand. That new layer does two things. It shields the print from being trampled, and it turns the footprinted surface into a boundary between layers, a horizon that geology can recognize and track. Over time, this stack of thin, alternating layers of wet and dry sediment accumulates. Track surface, cover layer, track surface, cover layer. Each one is a snapshot of a day, or maybe a season, when conditions were perfect for recording movement. Lake chemistry and groundwater movements slowly cement those layers, gluing the grains together with microscopic films of minerals. The prints go from soft impressions to hardened trace fossils, hidden inside what now looks like a simple, banded deposit. And there they sit. For thousands of years, they're nothing but subtle variations in density and porosity inside the rock. To get them back, you need another sequence of lucky breaks, this time in reverse. The lake has to shrink or disappear, exposing old lakebed to the air. Erosion has to start cutting down through the stack of layers, shaving off the overburden and skimming across those buried track horizons. If you remove too much, the prints erode with the rest. If you remove too little, you never see them. White Sands is basically sitting at that exact sweet spot. Wind is planing across the Pleistocene lake deposits, trimming them like a giant belt sander, and every so often it slices right through a trackway. That's why the landscape looks like a revelation machine and a shredder at the same time. The same wind that exposes the prints also sets a countdown timer on them. As soon as the track surface hits daylight, it starts to deteriorate. Salt crystallizes. moisture cycles cause microcracking. Grains loosen along the delicate walls and heels and toes. A single storm can erase a trackway that lasted 20,000 years underground. So when researchers at White Sands talk about ephemeral track surfaces, they're not being poetic. They're describing a brutal reality. Some of the most important evidence in the entire debate might only exist in recognizable form for months, maybe a few seasons, before it's gone. That's why documentation isn't an afterthought. It's the whole ball game. If you're trying to squeeze every last bit of information out of a trackway, you need to capture much more than, hey, here's a footprint. You're recording geometry, the exact shape and size of each print, down to tiny variations in arch and toe placement. You're recording orientation, how prints line up across the surface, whether someone is walking straight, weaving, changing pace, cutting across animal tracks. You're also recording depth profiles, how deeply the heel sank compared to the toes, how the weight shifted through the step, whether the substrate stiffened or softened along the path. Even subtle changes in depth can signal whether someone was carrying a load, speeding up, limping. And then there's context in the layers. Which lamination does the track cut into? What's above it? What's below? Are there fine crossbeds that show wind direction? Are there ripple marks from waves? Are seeds, pollen, or snail shells locked into the same horizon? Those vertical relationships are what tie individual steps to a broader environmental and chronological story. Doing all that with tape measures and hand sketches would be agonizingly slow and imprecise. This is where 3D scanning changed the game. At White Sands, teams use high-resolution photogrammetry and laser scanning to capture track surfaces in dense point clouds. In practice, that means they can create digital models where every little undulation of the footprint is preserved in 3 dimensions, at millimeter or even sub-millimeter scale. Those models can be flipped, sliced, color-coded for depth, analyzed for pressure patterns, even compared mathematically to other trackways. More importantly, they exist long after the wind has done its worst. A print that has been physically destroyed can still be studied, shared, remeasured, and reinterpreted by people who weren't even born when it was first uncovered. That digital afterlife raises an uncomfortable question. If we can scan a trackway in exquisite detail, should we always excavate it fully? On the one hand, excavation can damage surfaces. Anytime you dig, you're disturbing a system that was stable for thousands of years. You can collapse edges, change moisture regimes, trigger new fracturing. On the other hand, if you leave track surfaces buried, natural erosion will eventually expose and erase them, whether you've documented them or not. Field teams have to navigate that tension constantly. Do you peel back a large area to reveal long sequences of steps, accepting that the exposed parts will deteriorate faster? Or do you work with smaller windows, scanning and sampling intensively, but leaving most of the horizon intact for some future technology to examine more gently? There's also the question of triage. Some track surfaces show rare behaviours: a child running, a person carrying a heavy load, interactions with animals. Others are more routine. Do you prioritise the unusual ones for full excavation, or prioritise the best preserved layers regardless of what they show? There's no universal rulebook. Every decision plays out under the ticking clock of erosion and the practical limits of funding, time, and personnel. All of this means that future discoveries at places like White Sands may depend less on digging deeper and more on watching more carefully. As climate shifts, as droughts lengthen and storms intensify, landscapes are changing at speeds that would have stunned earlier geologists. Lakebeds dry out, dunes migrate, coastlines retreat. Each of those changes is an opportunity for buried traces to emerge and a threat to their survival. So instead of imagining the next big find as a single heroic excavation, picture a network of quiet observers and instruments. Repeat drone surveys that pick up subtle changes in surface texture, automated cameras that flag newly exposed layers, satellite data that shows where erosion has accelerated, local land managers trained to recognize the telltale patterns of track surfaces. The white sands footprints weren't a one-off miracle. They were one lucky intersection in a long, fragile life cycle. Imprint, drying, burial, cementation, re-exposure, documentation, or loss. Understanding that cycle doesn't just help us interpret the tracks we've already found. It tells us where to look next, how fast we need to move, when the ground starts telling its stories, and how easily those stories can blow away. When the ground starts telling its stories, there's another truth we have to face. Those stories don't just belong to science. White Sands sits in the homeland of native peoples, whose ancestors have lived in the region far longer than archaeology has had a name for it. Long before anyone talked about Beringia or Clovis, there were already stories about emergence, migrations, great floods, monster animals, changing lakes and sacred places. Those aren't carbon dates. They're not stratigraphic profiles. But they are history's ways communities have remembered their relationship with this landscape across hundreds, maybe thousands of generations. So when scientists say, "We found evidence that humans were here 23,000 years ago," they're not just speaking into a vacuum. They're speaking into a world where indigenous nations have been saying, in different ways, "We have always been here." This is where the phrase "First Americans" gets tricky. On the surface, it sounds simple. Find the earliest site, crown its occupants the first. But that framing carries political weight. For indigenous peoples whose land rights, sovereignty, and cultural survival are still contested, the idea that science might someday identify a different first people isn't just an abstract intellectual puzzle. It can feel like a potential weapon. There's a long, ugly history of outsiders using archaeology to undermine indigenous claims, arguing that mysterious earlier races built the mounds or that current nations are just recent arrivals with no real ties to the land. The specifics change, the pattern doesn't. When you treat deep time as a competition for primacy, who got here first, whose ancestors really count, you open the door for those arguments to come back in newer, supposedly more scientific clothes. That's why responsible storytelling about White Sands has to be careful with its language. These footprints don't prove that any particular modern group is descended from the track makers. They don't tell us tribal names, languages, clan systems, or ceremonial practices. Genetics, linguistics, and archaeology can sometimes sketch out big-picture relationships, shared ancestry, population splits, long-range migrations, but they can't say, this specific person walking along the shoreline was an ancestor of the X nation and not the Y nation. If someone claims that, they've left science behind. What the evidence can speak to is timing and environment. It can tell us that humans were present in southern North America during the last glacial maximum. It can show that they were moving through wetlands, sharing a landscape with mammoths and giant ground sloths. It can hint at behaviour, adults travelling with children, people returning to the same routes again and again. What it can't do is adjudicate identity claims among living peoples. It can't settle questions of belonging, sovereignty, or spiritual connection. Those are political, ethical, and cultural questions, not radiocarbon problems. So, how do you study a site like White Sands without repeating old mistakes? One answer is collaboration that isn't just symbolic. Archaeologists can and increasingly do work with tribal governments and cultural offices from the earliest stages, before permits, before sampling, before a paper gets drafted. That can mean co-developing research questions, so the work doesn't just satisfy academic curiosity, but also addresses indigenous priorities, sacred site protection, education, or land management. it can mean shared stewardship of data. Instead of treating digital models and sample archives as the exclusive property of universities or labs, they can be managed under agreements that give tribes a say in how they're used, who accesses them, and how long they're kept. And it definitely means rethinking how we talk about the ancient people themselves. Because there's a subtle trap built into a lot of scientific writing. We talk about early occupants, hunter-gatherer bands, pre-Clovis populations as if they were anonymous test cases in some grand experiment. Stripped of names, kinship, obligations and values, they become puzzles to be solved rather than communities that lived, loved, argued, raised children, buried their dead and made sense of their world. The white sands footprints make that harder to ignore. When you see a child's smaller tracks weaving through adult steps, or a person detouring around a mammoth path, it's hard not to imagine personalities, relationships, bad days, private jokes. These weren't data points, they were people. Keeping that in mind changes the tone. Instead of saying, "These are the first Americans," you can say, "These are the earliest securely dated human footprints we've found so far in North America." Instead of, "This discovery rewrites Indigenous history," you can say, "This discovery adds a new line of evidence to a much older, ongoing story that Indigenous peoples have carried in their own ways." That shift might sound small, but it matters. It signals that science is one way of knowing, not the only one. It leaves room for oral traditions without pretending they're just waiting to be confirmed by lab work. It acknowledges that living peoples have more at stake here than anyone else. In the end, responsible storytelling about the White Sands footprints means holding two truths at once. One, this is an extraordinary scientific find that pushes back the timeline of human presence in the Americas and forces researchers to rethink long-standing models of migration. Two, it sits inside a landscape of living nations whose histories don't begin with our dates, whose identities aren't up for external validation, and whose ancestors, however deep in time, deserve to be treated as more than anonymous shadows walking across an ancient shoreline. If we can keep both truths in view, then when we ask what these footprints prove, we're not just asking what they do for our theories. We're asking what our theories do to the people whose lands we're walking on. So where does all of this leave us? Are the White Sands footprints proof that humans were in North America 10,000 years earlier than we thought? It depends what you mean by proof. Let's start with what's on the firmest ground. First, the sheer abundance of trackways. We're not talking about a single partial print that might be a weird erosion pattern if you squint hard enough. We're talking thousands of human footprints, spread across multiple surfaces in multiple layers over a wide area. Adults, teenagers, kids, outbound journeys and return trips. Overprints with mammoths and giant ground sloths. If you removed every radiocarbon date from the equation, you'd still be left with overwhelming evidence that humans were using this landscape repeatedly over a span of time, not just passing through once. Second, the stratigraphic context. The prints aren't random impressions floating in space. They sit in a stack of lakebed sediments that read like pages in a book, older below, younger above. Human tracks appear in particular layers. Seeds and other organic fragments are locked into those same layers. Volcanic ash beds and other markers help tie those layers into broader regional timelines. When everything is undisturbed and consistent across a wide area, that's powerful. It means you're not just dating isolated objects, you're dating a whole environment. Third, the multi-method dating efforts. The initial claims leaned heavily on radiocarbon dates from ditch grass seeds. Critics pushed back, arguing that old carbon dissolved in lake water could make those seeds look thousands of years older than they really were. That's the reservoir effect problem. Instead of ignoring that, the team and other researchers went back in with more tools. They dated quartz grains using luminescence methods, which measure when those grains last saw sunlight. They dated other types of organic material, not just one plant species. They looked at pollen, geochemistry, and regional climate signals to see whether the lake levels and environments implied by the sediments matched what we'd expect during the last glacial maximum. Those independent lines of evidence don't all land on the exact same calendar year. That's not how this works, but they cluster in the same broad window. Humans in this basin roughly between 23,000 and maybe 20,000 years ago, give or take, deep inside the last ice age, now for the wobblier parts. The reservoir offsets haven't been pinned down perfectly. We know ancient Lake Otero probably recycled some old carbon. The question is, how much? A few hundred years? A couple thousand? More different models give different answers and they don't all agree. That means any single radiocarbon date on those aquatic plants comes with a built-in maybe attached. There's also the issue of correlation. When you date a seed or a pollen sample, you're dating that object, not the footprint itself. You're assuming that the seed was deposited at essentially the same time as the track was made, and that the sediment hasn't been disturbed since. The stratigraphy at White Sands looks clean, but no site is perfect everywhere. Even small amounts of mixing can smear events in time. Then there's simple resolution. Earth scientists are pretty good at saying, this layer is from the peak of the last glacial maximum, or this layer belongs somewhere in the late Pleistocene, getting down to, this footprint was made in the year 21,467 BCE, in October on a Thursday, is not happening. Even distinguishing 23,000 from 21,000 years ago is hard, when your tools have error bars of hundreds of years or more. So how can confidence be high if the exact numbers can still shift? Because for the big questions, you don't actually need pinpoint precision. Imagine a target with 3 rings, younger than 14,000 years, between about 18,000 and 14,000, and older than 20,000. Those rings map onto different migration scenarios, late arriving Clovis-first, somewhat earlier pre-Clovis, and truly glacial maximum occupation. Every serious attempt to date the White Sands Trackways keeps hitting that outer ring. Even if you accept a substantial reservoir effect and push the radiocarbon ages younger, they still land well before the 13,000 14,000 year mark that used to define the earliest secure presence. The luminescence dates, which aren't affected by lake carbon, independently support a last ice age time frame. The lake level history and regional climate reconstructions point in the same direction. Could the dates tighten? Absolutely. Could the central estimate move a bit, say from 23,000 down to 21,000, or up to 24,000, as methods improve and more samples come in? Very likely. But that kind of shift doesn't collapse the core claim. It doesn't turn humans here during the Ice Age back into humans only appear after the Ice Age. It just refines the when inside an already surprising window. What would really strengthen the case? More independent dates from more techniques on more materials. Luminescence ages from multiple layers that contain both human and animal tracks. Radiocarbon dates not just on aquatic plants, but on terrestrial material that isn't affected by lake water carbon in the same way. Perhaps uranium series ages from carbonates, or other isotopic clocks that don't share the same vulnerabilities. Clearer geochemistry of the lake system, direct measurements and modelling of how much old carbon the water was actually carrying at different times. That would let researchers correct the radiocarbon dates with more confidence, instead of bracketing them with broad possibilities. And wider sampling. Right now, the most detailed work focuses on a few heavily studied trackways. Surveying more of the basin and more sites beyond White Sands could show whether these dates line up with other evidence of human presence across the region. Footprints in one ancient lake are powerful. Footprints, artifacts and campsites scattered across a continent in the same time window would be overwhelming. All of this feeds into that headline-ready phrase, 10,000 years earlier than we thought. Used carefully, it's a useful shorthand. It captures the scale of the shift from the old Clovis-first model, but it also freezes the story in a way that science itself doesn't. Our earlier than we thought is always provisional. If White Sands eventually settles at 21,000 instead of 23,000, the number changes. If another site turns up with equally strong evidence at 26,000, the number changes again. The real point isn't the exact figure, it's that the range of plausible timelines has opened up. And that has consequences well beyond bragging rights over who gets to plant the first flag in prehistory. If humans were living in southern North America during the last glacial maximum, then the old simple migration stories don't work anymore. You can't just have a rapid sprint through an ice-free corridor that opens late, followed immediately by Clovis points everywhere. You have to think about coastal routes, about people travelling along shorelines now drowned under the Pacific. You have to think about small, scattered groups adapting to radically different environments over thousands of years, tundra, steppe, wetlands, deserts forming and draining. You have to rethink how quickly people can move, how flexible their technology really was, how they managed to support children and elders in landscapes we usually imagine as empty and hostile. You have to model population growth, isolation, and mixing over a much longer span of time. And you have to see the Americas not as a last-minute add-on to human history, but as a theatre where experimentation in adaptation, tool-making, and social organisation was playing out, while ice sheets still dominated the north. That's why the debate over White Sands matters, even if the dates shift by 1,000 years here or there. It's not a scoreboard question. It's a question about what humans are capable of, how early, how often, and how creatively we've stepped into new worlds and figured out how to stay. So, if White Sands has cracked the door open, what happens when we really start pushing on it? The first thing to realise is that White Sands probably isn't a one-off miracle. It's a spectacular case where geology, climate, and sheer luck lined up to preserve a ghostly record of passing feet. But the processes that created Lake Otero, its shorelines, and those mudflats weren't unique. Across the western United States and northern Mexico, the last ice age built whole chains of similar basins, ancient lakes, playas, and wetlands that have long since dried or shrunk. Think of the old pluvial lakes in Nevada and Utah, the basins of the Great Basin and the High Plains, the shorelines etched around extinct lakes in the Mexican interior. Anywhere you had persistent shallow water, fine sediments, and alternating wet and dry periods, you had a potential footprint factory. If humans were in southern North America during the last glacial maximum, they didn't beam directly into White Sands and vanish. They would have followed water and resources. That means other ancient shorelines, marsh margins and low-lying flats are logical next places to look for similar tracks, or for the camps and activity areas that go with them. And then there's the biggest missing piece of all, the coast. Every model that takes White Sands seriously has to make peace with a coastline that looked radically different 20,000, 25,000 years ago. Lower sea level exposed a vast, now submerged landscape along the Pacific Rim. River mouths were farther out. Coastal plains and estuaries that would have been rich in food are now drowned tens of meters below the modern shoreline. If people were using a Pacific coastal route, a huge chunk of the story is literally underwater. That's where marine geophysicists and underwater archaeologists come in. High-resolution seafloor mapping, sub-bottom profiling, and targeted coring on continental shelves could start to pick out buried river channels, paleo shorelines, and drowned terraces that once would have been dry land. Those are the equivalents of Lake Otero, just under the waves. Finding stone tools or habitation structures out there is hard. But even in direct evidence, charcoal layers, unusual sediment chemistry, preserved pollen, matching terrestrial vegetation, could flag places worth more detailed exploration with ROVs and divers. On land and under the sea, the toolbox is changing fast. You're going to hear a lot more about things like improved luminescence dating, sediment DNA, microstratigraphy, and high-resolution geochemistry in this debate. These sound like technical footnotes, but they're exactly the kinds of methods that turn maybe into, we're pretty sure, better OSL and related protocols can tighten the ages on the grains of sand that bury a footprint or an artifact. Laboratories are getting better at checking whether grains were fully reset by sunlight, screening out disturbed samples, and stacking dozens of dates through a sequence instead of relying on a few. Sediment DNA, scraps of genetic material preserved in mud and sand, can reveal which plants and animals were actually present, even when bones and macrofossils are gone. Imagine coring an old lakebed and being able to say, mammoth DNA here, sagebrush here, freshwater algae here, human DNA, maybe here. It's early days, and contamination is a huge issue, but the potential is enormous. Microstratigraphy and high-resolution geochemistry let researchers read the layers between the layers. Tiny changes in grain size, mineral content or isotopes can show whether a surface was exposed for a long time, whether it was reworked by floods, whether it sat under clear water or dried in the sun. That's critical for questions like, did this footprint surface stay intact, or was it churned and smeared over centuries? Put together, these techniques turn a flat stack of mud into a detailed environmental logbook. By the way, if you're into this kind of deep time mystery, you might like the book we put together on 12 unexplained discoveries from human prehistory. You can grab it on the website. There's a link in the description. And there's a discount running this week if you want to dive deeper between videos. So where will scientists actually go next? Expect more systematic surveys of other Pleistocene basins, LiDAR and satellite reconnaissance to map subtle shorelines, followed by on-the-ground probing for trackways, hearths, and buried surfaces. Expect cores pulled from old deltas and floodplains in Central and South America, trying to spot the first reliable signatures of human burning, erosion, and ecological change. Expect teams arguing over whether a certain layer of charcoal and pollen shift really means people, or just natural fire and climate. Climate and hydrology models are going to be doing quiet but crucial work behind the scenes. If you can reconstruct where water stood during the last glacial maximum, where lakes expanded, where wetlands formed, where springs emerged at the edge of ice or desert, you can narrow the search. Early groups needed reliable water, fuel, and food. They didn't scatter randomly across the map. They followed patterns that climate physics can still help us see. Those models can also test white sands itself. If Lake Otero was the size and depth the sediments suggest at 23,000 years ago, do the lake levels, salinity, and shoreline positions match the story told by the footprints and plant remains? If a radically different age scenario is proposed, does it still fit the climate and hydrology that other data demand? When interpretations and models disagree, something has to give. And that brings up an uncomfortable but important point. What could actually overturn the current reading of white sands? One possibility is new dating work that shows severe, localized disturbance in the footprint layers, evidence that the surfaces have been mixed in ways that make them unreliable time markers. Another would be a robust, independently calibrated reservoir model that demonstrates the seeds must be thousands of years younger than their raw radiocarbon suggests, and that the luminescence ages somehow map onto different younger events. More dramatically, someone could find equally well-preserved human tracks or undeniable artifacts in the same basin. but clearly tied to much younger sediments above the supposed footprint horizons in a way that forces a complete rethink of the local stratigraphy. On the flip side, the most likely outcome isn't a collapse, it's a refinement. Dates tightening by a millennium here, a reconstructed shoreline shifting a few kilometres there, an updated reservoir offset that nudges the fingerprints a bit younger or older but leaves them squarely inside the Ice Age. Which means, for now, the smartest stance to take isn't settled forever or obviously wrong. It's provisional. Science at this timescale moves at the speed of field seasons, grants cycles and permit approvals. Excavations can't just bulldoze a national park. Core samples take months to process. Dating labs have backlogs. Papers go through review, get critiqued, get revised. Replication takes time, especially when you're dealing with fragile footprints that literally erode a little more every year. So the challenge for researchers and for the rest of us is to live with that in-between space. Hold the white sand story as a working model. Humans in southern North America during the last glacial maximum, probably using routes and strategies that our textbooks didn't discuss a generation ago. Watch how that model fares as new data arrive from other lakes, other shorelines, and maybe even from the drowned edges of the continent. And be ready to update. If the evidence stacks up, the early presence becomes less controversial and more like background knowledge, of course people were here by then. If it falters, then the timeline slides back toward later arrivals, and we learn something important about how easy it is to misread the deep past. Either way, the footprints have already done their job. They've forced us to ask better questions, to look in new places, and to admit that our neat stories about when humans got here are always drafts, never final editions. And that brings us back, finally, to the people themselves. The ones who left those marks in the mud, not to make a point about migration theories, but simply because they had somewhere to go. So what, exactly, can we say about them? Not in the poetic sense, but in the careful, what does the evidence really support sense? White sands doesn't yet prove that humans were in the Americas 30,000 or 40,000 years ago. It doesn't rewrite every part of the peopling story in one stroke. What it does most credibly is show that by around the last glacial maximum, there were already people moving through what is now southern New Mexico, returning to the same shoreline over and over, with children, with loads, with purpose. It demonstrates presence, it demonstrates repetition, it demonstrates behaviour, and footprints do this in a way that almost nothing else can. Stone tools can drift downslope or wash into younger deposits. Bones can be dragged by scavengers, reworked by floods, gnawed and scattered, until their context is a mess. Radiocarbon dates can be skewed by old carbon and reservoir effects. But a footprint is different. It's an interaction between a specific body and a specific surface on a specific day. Your heel sinks a little, your toes push off. If you're tired or injured, the angle shifts. If you're carrying a child, the spacing changes. If you're running, the mud splays out differently. All of that is recorded in a few millimetres of compacted sediment that, if conditions are just right, hardens, gets buried, and survives for tens of thousands of years. That's why the White Sands Trackways feel so immediate. They aren't just evidence of humans. They are evidence of humans doing things, walking parallel to mammoths, cutting across giant sloth trails, looping back along the same path again and again. They turn, were people here, into what were they doing when they were here? At the same time, they don't answer everything. They don't tell us which route those people took to get into the continent. They don't tell us whether their ancestors had been here for millennia already, or had just arrived a few generations before. They don't settle debates about Clovis-first versus pre-Clovis versus multiple waves. Instead, they sit inside that bigger picture, as a strong, puzzling data point. Humans on a Pleistocene lakeshore at a time when ice sheets still loomed to the north, likely using strategies and pathways our older models either downplayed or missed entirely. So how do you, as a non-specialist trying to follow all this, navigate between excitement and skepticism? A few simple habits go a long way. Pay attention to methods, not just headlines. Are claims based on a single technique, or have multiple independent dating approaches converged on the same answer? Do the authors explain possible errors and limitations, or do they wave them away? Are critics raising specific, testable issues, like reservoir offsets or stratigraphic mixing, or just saying, this feels wrong? Look for Replication. Has another team, using different equipment or sampling strategies, gotten similar results? When you see an article about some astonishingly early date, ask yourself, has this been confirmed anywhere else? Or is this one site carrying the whole argument on its back? And be comfortable with, for now, scientific stories at this timescale are always written in pencil. The goal isn't to guess the final answer, it's to track how the weight of evidence shifts over time. If you can do that, hold a sense of wonder in one hand and a willingness to revise your beliefs in the other, you're basically thinking like a scientist. The people who left those footprints didn't know they'd be dragged into our debates about migration routes and radiocarbon calibration curves. They were just living their lives in a hard, beautiful, changing world. Following their tracks back through time is a privilege. What we do with that privilege, whether we turn it into dogma or into better questions, is up to us. If you want to keep exploring those questions with me, make sure you like this video, subscribe to the channel, and hit the notifications so you don't miss what comes next. I'd love to hear where you're listening from. Drop your city, region, or country in the comments and let me know what you think about the White Sands evidence. And if this kind of deep prehistory fascinates you, there's a book on the website about 12 of the most intriguing prehistoric secrets we know of today. You can read more about it or grab a copy using the link in the description. Thanks for walking through the mud with me.